For a long time, astronomers assumed the Milky Way was more or less drifting peacefully within the local group, its movement determined by the gravitational interactions with nearby galaxies such as Andromeda and the smaller satellite galaxies scattered around us. But by the late 20th century, a peculiar finding began to unsettle this simple picture. The Milky Way appeared to be moving through space much faster than gravitational models predicted. It wasn't a gentle drift. It was a determined, measurable, large-scale motion, one that required an explanation far beyond the boundaries of our galaxy. If the thought of hidden cosmic giants dragging the Milky Way through space captures your imagination, subscribe now. Our journey to uncover what's driving this massive motion starts today. This revelation didn't come from watching stars or nearby galaxies, but from an unexpected source: the cosmic microwave background, or CMB. The CMB is the faint glow left over from the Big Bang, bathing the universe in microwave radiation that is nearly uniform in all directions. Astronomers studying this radiation noticed something odd. Instead of a perfectly even temperature pattern, one side of the sky appeared slightly warmer, while the opposite side looked slightly cooler. The temperature difference was small, about 1 part in 1,000, but unmistakable. This asymmetry was the first hint that the Milky Way, along with the rest of the local group, was moving relative to this ancient light. To understand why this mattered, it's important to recognize that the CMB acts like a reference frame for the entire universe. It is the oldest observable signal we have, dating back 380,000 years after the Big Bang, and it permeates all directions. If a galaxy is stationary relative to this background, the CMB will look the same in every direction. But if it is moving, photons coming from the direction of motion are slightly compressed, appearing hotter, while photons from the opposite direction are stretched and appear cooler. This effect is known as the CMB dipole anisotropy. By the early 1980 seconds, data from balloons, ground-based telescopes, and early satellite observations all pointed to the same conclusion. The Milky Way was rushing through space at approximately 600 kilometers per second, or about 2.2 million kilometers per hour. This was not the speed of stars orbiting the galactic center, which average around 220 kilometers per second. It wasn't the orbital motion of the Milky Way within the local group. It was an entirely separate motion, one affecting the whole region of space our galaxy occupies. Astronomers knew that something big had to be pulling or influencing the Milky Way. But the identity of this force was not at all obvious. The first suspicion was Andromeda, our nearest spiral galaxy. At about 2.5 million light-years away, and with a mass similar to the Milky Way's, it exerts a gravitational influence that is pulling both galaxies toward an eventual collision 4 billion years from now. But Andromeda could only account for a few hundred kilometers per second at most, and its pull was directed toward a different region of the sky than the CMB dipole indicated. The numbers simply didn't line up. Next came the Virgo cluster, a large assembly of more than 1,000 galaxies located roughly 50 to 60 million light-years away. The Virgo cluster is massive, trillions of times the mass of the Sun, and its gravitational pull certainly affects the Milky Way. But even that wasn't enough. When astronomers calculated the expected velocity based on Virgo's mass, the result fell short by hundreds of kilometers per second. The early models couldn't account for nearly half of the Milky Way's observed motion. This meant something else, something far more powerful, had to be exerting a gravitational influence. In 1986, an influential study led by astronomers Alan Dressler, Sandra Faber, Donald Lynden Bell, and their collaborators introduced a new idea: the Great Attractor. This hypothetical concentration of mass appeared to lie in the direction of the constellations Centaurus and Hydra, and seemed to be drawing a vast number of galaxies toward it. The Great Attractor was estimated to be located roughly 150 to 200 million light-years away. But there was a problem. The region of sky where the Great Attractor resides is heavily obscured by dust and stars in the plane of our own galaxy. This area, known as the zone of avoidance, blocked traditional optical observations, making it challenging to map the structure properly. Still, the evidence indicated that the Milky Way was being pulled toward a large mass concentration located outside the immediate local group. Subsequent observational campaigns aimed to better characterize this region using improved instrumentation. During the 1,990 seconds, the launch of the Cosmic Background Explorer, or COBE satellite, allowed scientists to map the CMB with unprecedented precision. COBE confirmed the dipole anisotropy measurements and provided even more accurate values for the Milky Way's motion. The numbers were solid. The Milky Way and the entire local group were moving at around 630 kilometers per second relative to the CMB. At this speed, we travel across a typical light year in about 500 years, a comparatively short time on cosmic scales. But COBE's data also indicated something else. The direction of this motion did not point exactly at the Great Attractor. It was close, but not perfect. This hinted that there were additional influences beyond the Great Attractor's region, possibly from even larger structures lying far beyond the obscured region of the sky. The mystery deepened with additional observations from the Wilkinson Microwave Anisotropy Probe, or WMAP, in the early 2000s. WMAP refined CMB measurements and confirmed the Milky Way's high-speed motion with remarkable accuracy. It also provided better maps of the temperature variations across the sky, allowing astronomers to construct more detailed models of the gravitational environment around our galaxy. Around this time, new radio and infrared surveys began to peer through the zone of avoidance. Instruments like the Parkes Radio Telescope in Australia, working with the H.I. Parkes All-Sky Survey, or HIPAS, detected hydrogen gas emissions from galaxies hidden behind the dust. The 2-micron All-Sky Survey, or 2MASS, used infrared wavelengths to reveal galaxies previously invisible to optical telescopes. These surveys began to fill in the missing pieces, showing that the region around the Great Attractor was far more populated with galaxy clusters than previously realized. Yet even as more galaxies were discovered, another surprising revelation emerged. The mass of the Great Attractor still wasn't enough to account for the Milky Way's velocity. Large structures like the Norma cluster and the Hydra Centaurus supercluster contributed to the pull, but calculations continued to fall short. Something beyond these structures had to be influencing our motion. By the mid-2000s, astronomers began to look further out into space, beyond the Great Attractor. When they did, they discovered something extraordinary. The Shapley supercluster, a massive concentration of galaxy clusters located more than 500 million light-years away. This supercluster contains some of the most massive galaxy clusters known, including Abell 3558 and Abell 3562, each with tens of thousands of galaxies. Its total mass is estimated to be around 10 million billion times the mass of the Sun, making it one of the largest known structures in the local universe. The Shapley supercluster became a new candidate for contributing to the Milky Way's motion. Its position on the sky aligns closely with the direction indicated by the CMB dipole, and its mass provides a substantial contribution to the observed velocity. However, calculations indicate that additional components are required to fully account for the motion, based on residual velocities detected in observational datasets. Researchers also considered the possibility, based on analyses of large-scale velocity fields, that gravitational influences might originate from structures located beyond the region currently observable. Observations of coherent motions in galaxy clusters across large volumes of space were grouped under the term dark flow. These results were debated within the cosmology community because of their implications for existing theoretical models. By the time the European Space Agency's Planck satellite began collecting data in 2009, multiple observational programs had identified large-scale contributions to the Milky Way's motion. Planck produced high-resolution CMB maps, refining the dipole anisotropy measurements and providing more precise constraints on the direction and magnitude of the local group's velocity relative to the CMB. These measurements confirmed earlier observational results and showed that some components of the motion remain insufficiently explained by known mass concentrations. Mapping galactic drift, the tools that exposed the movement. When the realization emerged that the Milky Way was racing through space at a speed unaccounted for by nearby structures, astronomers faced a daunting challenge. Measure this movement precisely and determine where it was coming from. But galaxies do not leave trails behind them, and they cannot be followed like ships crossing an ocean. Their motion must be inferred indirectly through light and radiation that often travels millions or even billions of years before reaching Earth. To unravel the Milky Way's mysterious drift, scientists needed to build instruments capable of measuring distances, velocities, and angular shifts with levels of accuracy that would have been unthinkable only decades before. The groundwork for these efforts began with optical observations, but optical telescopes alone were insufficient. Dust, gas clouds, and highly energetic objects within the Milky Way's disk distort, or entirely block visible light, leaving enormous gaps in sky surveys. To bypass these limitations, astronomers turned to wavelengths that could travel through cosmic obstacles more effectively. Radio waves, infrared light, and microwave frequencies became essential. They allowed scientists to see through regions of the sky that were once impenetrable, exposing galaxies and structures that had been hidden for billions of years. One of the earliest breakthroughs came from radio astronomy. By the mid-20th century, radio telescopes had become powerful tools for mapping the positions and motions of distant galaxies. But radio measurements reached a new level of precision with the development of very long baseline interferometry, a method that uses radio telescopes separated by thousands of kilometers to create an effective dish the size of Earth. The technique relies on linking observatories across continents, synchronizing them with atomic clocks accurate within billionths of a second. When their data are combined, the resulting resolution is sharp enough to detect shifts in celestial positions smaller than the width of a coin seen from thousands of kilometers away. This method, known as VLBI, allowed astronomers to measure the positions of quasars, extremely distant galaxies, with active, supermassive black holes at their centers, with extraordinary precision. Because quasars lie so far from the Milky Way, some more than 10 billion light-years away, they serve as nearly fixed reference points. Any observed shift in their apparent position indicates movement of the Earth, the solar system, or the entire Milky Way. These measurements helped refine the velocity of the local group and produced an increasingly accurate frame of reference for tracking the galaxy's motion through space. But even VLBI had limitations. Measuring the Milky Way's movement required comprehensive data on the motions of individual stars and nearby galaxies, something optical methods were better suited for. However, early optical surveys lacked the precision needed to measure tiny angular shifts in star positions over time. That changed dramatically in 1989, when the European Space Agency launched the Hipparcos satellite. Hipparcos was the first mission dedicated specifically to high-precision astrometry. The branch of astronomy focused on measuring positions and motions of celestial objects. Over its 4-year mission, Hipparcos measured the positions, brightness, and distances of more than 100,000 stars with unprecedented accuracy. Though Hipparcos was not capable of mapping the Milky Way's large-scale drift directly, its results were essential for creating a more detailed model of the galaxy's internal motion. These data helped astronomers distinguish the Milky Way's rotation from its overall motion through the universe, providing a clearer picture of the galaxy's true trajectory. The next major leap came with the launch of WMAP in 2001. While the COBE satellite had produced the first large-scale maps of the cosmic microwave background, WMAP refined them dramatically. It provided temperature measurements of the CMB at a resolution nearly 30 times sharper than COBE's, allowing scientists to pinpoint the direction and magnitude of the dipole anisotropy with high precision. WMAP's measurements reduced uncertainties in the Milky Way's velocity to within a few kilometers per second, confirming the presence of a large-scale motion relative to the CMB. WMAP also revealed subtle fluctuations in the CMB that helped define the geometry and composition of the universe. These measurements confirmed that the universe is dominated by dark energy and dark matter, which together account for more than 95% of all mass energy. Understanding these components was crucial for modeling the gravitational environment around the Milky Way. While WMAP was transforming cosmology, infrared astronomy was opening new windows through the Milky Way's obscuring dust. The 2-micron all-sky survey, completed in 2001, used infrared wavelengths around 2 microns to penetrate regions of the sky previously hidden in optical light. 2MASS mapped more than 300 million stars and millions of galaxies, revealing structures in the zone of avoidance that had been entirely invisible to optical telescopes. Infrared observations exposed galaxy clusters, filaments, and dense knots of mass that contributed to the gravitational landscape influencing the Milky Way's movement. As infrared surveys expanded, radio telescopes continued to excel at detecting hydrogen gas, the most abundant element in the universe. The H.I. Parkes All-Sky Survey, begun in the late 1992, used the 64-metre dish at the Parkes Observatory in Australia to catalogue more than 5,000 galaxies located behind the Milky Way's disk. Many of these galaxies were found in regions where optical and infrared surveys were limited, providing crucial information about mass concentrations that could influence galactic motion. But the most transformative instrument for mapping the Milky Way's motion arrived in 2013 with the launch of the Gaia spacecraft. Built by the European Space Agency, Gaia was designed to create a 3D map of the Milky Way at a precision never before achieved. While Hipparcos measured 100,000 stars, Gaia measured more than 1.5 billion. It can detect positional changes as small as a few tens of microarcseconds, roughly equivalent to observing a coin on the surface of the Moon. This precision allows astronomers to track the motion of stars, star clusters, and nearby galaxies with extraordinary accuracy. The resulting data provide one of the most detailed views of the Milky Way's internal dynamics ever created. Gaia's ability to measure stellar proper motions has been essential for separating the Milky Way's rotation from its overall trajectory and for refining distance estimates to star populations across the galaxy. Its data have been instrumental in determining the shape of the Milky Way's disk, the distribution of dark matter within the galaxy, and the movement of satellite galaxies such as the Large and Small Magellanic Clouds. These details help astronomers create more accurate models of the gravitational environment within and around the Milky Way, clarifying the direction of the galaxy's external motion. Gaia's measurements are especially important because they reveal how various components of the Milky Way behave relative to the galaxy's center. The motions of halo stars, globular clusters, and dwarf galaxies all contribute to a clearer picture of the galaxy's trajectory through space. These data help scientists identify discrepancies between observed motion and the motion predicted by gravitational models. Such discrepancies often point to previously unrecognized forces or structures influencing the Milky Way. While Gaia revolutionized astrometry, another technology transformed radio astronomy. In 2016, the 500-meter Aperture Spherical Telescope, or FAST in China, became the world's largest filled-aperture radio telescope. With its massive collecting area, FAST can detect faint radio signals from distant galaxies, pulsars, and neutral hydrogen clouds. It provides highly sensitive measurements of the distribution of matter across millions of light-years. FAST's data have been used to map hydrogen gas in regions of the sky where other instruments are limited, adding new detail to the cosmic structures that contribute to the gravitational field influencing the Milky Way. Other radio observatories, such as the Atacama Large Millimeter Array in Chile and the Square Kilometre Array Pathfinders in South Africa and Australia, have also contributed to mapping cosmic structures. These instruments detect emissions from cold gas, molecular clouds, and intergalactic material that reveal the distribution of mass in regions far beyond the Milky Way. Their data help connect the motions of galaxies to the underlying structure of the cosmic web. As these technologies advanced, astronomers developed new computational techniques to interpret the vast quantities of data they produced. Algorithms capable of processing billions of measurements allowed scientists to model the motion of galaxies across hundreds of millions of light-years. These models reveal how galaxies flow along gravitational gradients, following pathways shaped by the distribution of dark matter and hot gas. By analyzing these flows, researchers can trace the origin of the Milky Way's motion, identifying the distant regions of space that exert the greatest influence. Local forces aren't enough. Why-known gravity sources fail. For many years, astronomers assumed the sources influencing the Milky Way's movement must lie within the region of space known as the local group, or, at most, within the immediate neighborhoods of the Virgo supercluster. Gravity diminishes with distance, so significant gravitational pulls were expected from nearby massive structures. However, as instruments grew more precise and large-scale surveys expanded, measurements showed that local gravitational forces could explain only a fraction of the velocity derived from cosmic microwave background data. This discrepancy indicated that additional mass influencing the Milky Way had not yet been identified. The first place researchers looked was the local group itself, the collection of more than 50 galaxies bound together by gravity. Though the vast majority of these companions are small dwarf galaxies, two systems dominate the group: the Milky Way and the Andromeda galaxy. Andromeda, with a mass of roughly 1 trillion solar masses, exerts a strong gravitational pull on our galaxy. It is currently moving toward the Milky Way at about 110 kilometers per second and will collide with us in several billion years. This mutual attraction certainly contributes to the Milky Way's movement, but when astronomers performed detailed calculations, it quickly became evident that Andromeda's influence could not account for more than a small portion of the galaxy's overall velocity relative to the cosmic microwave background. To refine these estimates, researchers turned to measurements from Gaia VLBI arrays and ground-based spectroscopic surveys. These instruments help determine the orbital motions of stars in both galaxies, as well as the velocities of satellite galaxies like Triangulum and the Magellanic Clouds. After compiling these data, astronomers concluded that the local group's internal dynamics added only about 40 to 60 kilometers per second to the Milky Way's motion, far short of the more than 600 kilometers per second measured from CMB dipole observations. The numbers were too small and the direction did not match the observed trajectory. The next candidate was the Virgo cluster, a massive congregation of galaxies situated roughly 54 million light-years away. The cluster contains around 1,500 known galaxies and has a mass estimated at several hundred trillion times that of the Sunday. It is the anchor of the Virgo supercluster, which includes the local group among its outer regions. Because of its enormous mass, the Virgo cluster exerts a substantial gravitational pull on nearby galaxies, drawing them inward at speeds that can reach hundreds of kilometers per second. This inward motion, known as Virgo-centric flow, was observed in the redshift values of galaxies across the supercluster. However, calculations showed that Virgo's gravitational field could not account for the Milky Way's full velocity. When combined with the internal motion of the local group, the total still fell short by several hundred kilometers per second. The direction was slightly misaligned with the vector indicated by the cosmic microwave background, indicating that additional mass beyond the Virgo cluster contributes to the galaxy's motion. Attention soon shifted to the larger structures within the Virgo supercluster, particularly the filaments and clusters connected to the Hydra Centaurus region. The Hydra cluster, located around 160 million light-years from Earth, contains roughly 150 bright galaxies and even more faint ones. Meanwhile, the Centaurus cluster holds several hundred galaxies and is one of the densest nearby clusters. Together, these regions form part of a vast network of interlinked structures known as the Hydra Centaurus supercluster. Because of their combined mass, astronomers suspected they could be partially responsible for the Milky Way's movement. As more data arrived from sky surveys, the Hydra Centaurus region became increasingly interesting. Observations suggested that this region was the center of a gravitational anomaly affecting thousands of galaxies across hundreds of millions of light-years. This anomaly became known as the Great Attractor, and early studies estimated its mass at hundreds of trillions of solar masses. The Great Attractor appeared to be influencing not only galaxies in the Virgo supercluster, but also those beyond it, including the Milky Way. Yet this massive gravitational feature did not fully account for the Milky Way's velocity. The pull from Hydra Centaurus pointed roughly toward the direction of the galaxy's motion, but lacked the strength needed to accelerate it to more than 600 kilometers per second. Infrared surveys revealed that the Great Attractor was not a single structure, but a complex region of intertwined clusters, filaments, and gas clouds. When the total mass was recalculated, it still did not fully account for the Milky Way's observed velocity. The strongest gravitational sources in the nearby universe did not account for the observed motion. Additional mass influencing the Milky Way was expected to lie either behind the zone of avoidance or beyond the Virgo and Hydra Centaurus superclusters. Researchers began searching for underestimated or overlooked contributions within the local sheet, a flattened structure of galaxies including the Milky Way, Andromeda, and the Triangulum galaxy. The local sheet itself is part of a larger feature known as the local wall, a filamentary structure stretching across tens of millions of light-years. Although these regions contain significant mass, they are not massive enough to generate a velocity of several hundred kilometers per second on their own. The gravitational forces within the local sheet are strong enough to influence the motion of individual galaxies, but too weak to produce the large-scale flow observed by cosmologists. The search then expanded to the Virgo supercluster's immediate surrounding. Much of the mass influencing the Milky Way was believed to be distributed across the cosmic web, the vast network of filaments and voids that make up the large-scale structure of the universe. Galaxies and clusters form along these filaments, where dark matter is densest, while enormous bubble-like voids contain relatively little matter. The flow of galaxies often follows the arrangement of these filaments, drawn toward regions of higher mass density. Understanding these flows required mapping both visible and dark matter across hundreds of millions of light-years. One of the key breakthroughs in understanding mass distribution on these large scales came from surveys of galaxy redshifts. The Sloan Digital Sky Survey, along with the 2DF Galaxy Redshift Survey, mapped the positions and distances of hundreds of thousands of galaxies. These data revealed patterns in galaxy clustering that helped astronomers model the gravitational forces acting on regions like the local group. However, the results did not fully match the Milky Way's observed velocity. Although the cosmic web's influence was measurable, the mass distribution within the surveyed regions did not account for the full acceleration. Researchers also considered whether the local group might be located near the boundary of a large void, an extensive region of space containing relatively few galaxies. Voids affect motion by allowing galaxies near their edges to move away from the low-density area more rapidly. One such region, the local void, borders the local group and extends more than 100 million light-years in one direction. Measurements suggested that the local void might contribute tens of kilometers per second to the Milky Way's motion, but the values remained insufficient to match the observed velocity. By the early 2000s, astronomers had ruled out most local sources of gravitational influence. Neither the local group, the Virgo cluster, nor the Hydra Centaurus region alone could explain the Milky Way's movement. Even when these contributions were combined, they did not match the velocity derived from cosmic microwave background data. These findings indicated that additional mass influencing the Milky Way likely lay at greater distances or in regions that were observationally obscured. As surveys continued to improve, astronomers detected indications of a large superstructure beyond the Great Attractor, deeper into space and partially obscured by the zone of avoidance. Radio and infrared observations revealed a concentration of galaxy clusters spanning hundreds of millions of light-years. This region, known as the Shapley supercluster, became a major candidate for explaining the Milky Way's motion. Before evaluating the contribution of the Shapley supercluster, astronomers needed to determine how large-scale structures collectively influence galaxy motion across extensive distances. This required mapping not only galaxy positions, but also their directions and velocities. Achieving this involved surveying regions beyond previously studied volumes to measure motions on larger scales. The inability of local gravitational sources to explain the Milky Way's motion required astronomers to extend their observations to larger scales, exploring deeper regions of the cosmic web and identifying additional massive structures. Further investigation focused on distant regions that could contribute significantly to the galaxy's velocity. The discovery of large-scale cosmic flows. As astronomers expanded their search beyond nearby clusters and filaments that could not explain the Milky Way's speed, they identified patterns of galaxy motion extending beyond local gravitational influences. Galaxies were observed moving in coordinated streams across regions spanning hundreds of millions of light-years. These patterns became known as large-scale cosmic flows and represented measurable motions linked to mass distributions on very large scales. The first indications came from redshift surveys in the late 1970 seconds and early 1980 seconds. When astronomers measured galaxy velocities, they expected the motion to be largely explained by cosmic expansion described by Hubble's law. However, in several regions of the sky, galaxies exhibited velocities exceeding the predicted values by hundreds of kilometers per second. These deviations, called peculiar velocities, pointed to gravitational influences from regions without clearly identified mass concentrations. One of the earliest large-scale surveys to detect such anomalies was the Seven Samurai Project, a collaboration involving astronomers including Mark Davis, Sandra Faber, and Alan Dressler. The team studied the motions of more than 400 galaxies using redshift measurements combined with luminosity-based distance estimates. They identified a large number of galaxies across a region hundreds of millions of light-years wide, moving toward the same area of the sky. This motion could not be accounted for by known local structures and indicated the presence of an unseen mass concentration. These observations contributed to the identification of the Great Attractor, a region of gravitational influence located behind the plane of the Milky Way. Later, studies showed that the Great Attractor is a complex region rather than a single central mass. Its identification demonstrated that large-scale galaxy motions extend beyond the Virgo supercluster. As astronomers examined galaxy motions in greater detail, they found that the flow toward the great attractor was part of a larger pattern. Galaxy clusters were observed moving along filaments of the cosmic web toward mass concentrations that were still being mapped. These filaments extend across distances exceeding 300 million light-years and connect galaxy clusters into supercluster complexes. To map these flows, researchers used distance measurement techniques independent of redshift. One method involved analyzing brightness fluctuations in elliptical galaxies applied effectively in the 1,980 seconds. Another used the relationship between the rotational speed of spiral galaxies and their luminosity. These techniques showed that peculiar velocities occurred across continuous regions of the sky rather than in isolated locations. In the early 1,990 seconds, large-scale surveys such as the ESO SLICE project and the Las Campanas redshift survey expanded the known structure of the universe. They showed that galaxies are arranged in sheets and filaments surrounding large voids. The CFA Great Wall, discovered in 1989, extends more than 500 million light-years, and later surveys identified the Sloan Great Wall at nearly 1 billion light-years. These structures correspond to gravitational gradients influencing galaxy velocities. Deeper surveys capable of probing regions obscured by the Milky Way provided additional evidence. Instruments such as the infrared astronomical satellite, along with ground-based infrared observations, revealed galaxies in the zone of avoidance. These observations identified clusters, including the Norma cluster, a dense concentration of hundreds of galaxies located within what is now called the Norma supercluster. However, even as the structure of the great attractor became better defined, the gravitational influence estimated from this region did not fully account for the large-scale flows measured by redshift surveys. The observed motions indicated that additional mass concentrations beyond the great attractor were contributing to galaxy velocities over large distances. These suspicions were confirmed as surveys pushed farther into the southern sky. In the mid-1990 seconds, astronomers identified an enormous concentration of galaxy clusters in the constellation of Centaurus. This region, later recognized as part of the larger Shapley concentration, contained dozens of clusters and was far more massive than the Great Attractor. The discovery helped explain why the observed motion of the Milky Way did not point directly at the Great Attractor, but instead angled slightly beyond it. The Milky Way, along with thousands of other galaxies, was being drawn not just toward the Great Attractor, but past it, toward an even more massive supercluster lying more than 500 million light-years away. Measurements from the 6DF Galaxy Survey, which catalogued more than 125,000 galaxies in the southern sky, indicated that a substantial portion of galaxy motion across hundreds of millions of light-years is directed toward the Shapley concentration. The data showed consistent flow patterns aligned with gravitational gradients associated with the region. As astronomers continued to refine their measurements, they found that even the Shapley concentration did not fully account for all observed motions. Additional surveys, such as the Cosmic Flows projects, mapped galaxy velocities in greater detail. These studies combined distance measurements from thousands of galaxies to construct a three-dimensional velocity map of the local universe. The results showed that the Milky Way, along with many neighboring galaxies, was part of a flow extending over more than 1 billion light-years. These flows traced pathways along the cosmic web, following dark matter filaments that guided matter toward the densest regions of the universe. Large-scale flows were also detected in regions opposite the Shapley concentration, indicating gravitational influences from multiple directions. Some galaxies showed motion consistent with the gravitational effects of the local void, an underdense region adjacent to the local group. These influences are smaller in magnitude than those associated with more distant superclusters. Galaxy cluster motions, measured through distortions in the cosmic microwave background caused by hot intracluster gas, provided additional information. These measurements, extending beyond 800 million light-years, revealed coordinated motions across large regions of space. The observed flows indicated gravitational influences from structures more distant than the Shapley supercluster. The identification of large-scale cosmic flows showed that galaxy motions are influenced by mass distributions on very large scales rather than solely by local structures. These flows extend across regions much larger than previously mapped and align with gravitational gradients associated with distant attractors. Large-scale cosmic flow measurements connected local velocity observations with distant mass concentrations. The data indicated that the Milky Way's motion corresponds to gravitational influences from large-scale structures beyond the local environment. Continued mapping of these flows identified additional massive regions contributing to observed galaxy velocities beyond the Great Attractor, encountering the Shapley supercluster. As astronomers followed the immense galactic flows that extended well past the Great Attractor, they began to realize that they were being drawn toward something even more massive, something far beyond the boundaries of the Hydra Centaurus region. The large-scale motions mapped in earlier surveys did not converge at the Great Attractor as once assumed. Instead, the flow vectors continued beyond it, pointing deeper into the southern sky. This redirection was not subtle. The peculiar velocities of thousands of galaxies angled away from the supposed gravitational center, indicating that the real engine of cosmic movement lay farther out. The next step was to identify the colossal region responsible for this gravitational influence, a region that had eluded astronomers for decades. The earliest signs of this distant superstructure came from the Abell catalogue, compiled by astronomer George Abell in the late 1952. Abell had systematically classified thousands of galaxy clusters across the sky, ranking them based on richness and concentration. Among the clusters in the southern hemisphere, he noted an unusually dense region containing several exceptionally rich clusters, including Abell 3558, Abell 3560, and Abell 3556. Although the significance of this region was not immediately clear, later researchers recognized it as part of a much larger formation that would eventually be known as the Shapley supercluster. The scale of this supercluster was daunting. Early estimates suggested that it contained more than 20 massive galaxy clusters and hundreds of smaller ones. As technology improved, astronomers found that the number of clusters associated with the region was even greater than originally thought. Today, the Shapley supercluster is believed to contain more than 30 major clusters and thousands of galaxies, placing its total mass at around 10 million billion times that of the Sunday, yet size alone did not convey its full significance. What made the Shapley supercluster notable was its location, roughly 650 million light-years from the Milky Way, beyond the Hydra Centaurus region and outside the reach of earlier surveys. Observations showed that its gravitational influence extended across large distances, affecting the motions of galaxies in multiple clusters. These effects indicated that structures at such scales could shape galaxy movements along the filaments of the cosmic web. As researchers re-examined redshift surveys, they noticed that the most significant peculiar velocities pointed almost directly toward the Shapley region. The direction of the Milky Way's motion, inferred from the cosmic microwave background dipole, matched this same alignment, suggesting that Shapley played a major role in accelerating our galaxy. This agreement between velocity data and structural mapping strengthened the case that the Shapley supercluster was a prime contributor to the Milky Way's unusual speed. While astronomers had long suspected that structures larger than the Great Attractor must exist, the density and mass of the Shapley supercluster exceeded their expectations. The cluster Abell 3558 alone is one of the richest clusters in the nearby universe, hosting hundreds of massive galaxies and a hot intracluster medium detectable in both X-ray and radio wavelengths. Studies using the Rosat satellite and later the XMM Newton and Chandra observatories measured temperatures of the intracluster gas exceeding tens of millions of degrees. These temperatures indicated violent interactions among the galaxies in the cluster, including mergers of subclusters and complex shock fronts spreading across millions of light-years. Another key component of the Shapley region is the cluster Abell 3562, located near the center of the supercluster complex. This cluster contains a large population of elliptical galaxies and a central galaxy exhibiting signs of recent activity, such as extended radio lobes and disturbed gas flows. These features suggest that Abell 3562 is still accreting material from surrounding filaments, contributing to the ongoing growth of the Shapley supercluster. The filaments connecting these clusters form one of the densest cosmic structures identified in large-scale surveys. These filaments transport galaxies, gas, and dark matter towards central regions of high gravitational density, influencing the motions of surrounding galaxy groups. As surveys improved, astronomers determined that the Shapley region is part of a broader network that includes the Horologium Reticulum supercluster and several additional overdensities extending across nearly 1 billion light-years. The importance of the Shapley supercluster became even clearer when observations from the 6DF Galaxy Survey were completed in the mid-2000s. This project mapped the redshifts of more than 120,000 galaxies in the southern hemisphere, including many located along the pathways of cosmic flows leading to Shapley. The survey revealed that galaxies were moving toward the region from across enormous expanses of space, with flow velocities far exceeding the values predicted by models that included only local structures like Virgo or the Great Attractor. One notable discovery was that galaxies on the opposite side of the Great Attractor also showed motions consistent with the gravitational pull of the Shapley supercluster. This indicated that the Shapley region exerted a gravitational influence independent of the Hydra Centaurus structures. The data showed that Shapley is one of the most significant mass concentrations affecting galaxy motions within this portion of the cosmic web. The confirmation of Shapley's influence came from studies of the galaxy velocity field, particularly those compiled in the Cosmic Flows surveys. These projects combine distance measurements from thousands of galaxies to produce three-dimensional maps of cosmic motion. The maps revealed a strong velocity gradient pointing toward the Shapley region. Galaxies closer to Shapley moved faster in its direction, while those farther away still showed a measurable component of motion toward it. This gradient provided the clearest evidence yet that the Shapley supercluster was altering the movement of galaxies across an enormous region of space. As astronomers analyzed these data, they realized that the Shapley supercluster alone accounted for a substantial fraction of the Milky Way's anomalous velocity. Estimates suggested that Shapley contributed up to a quarter of the total speed observed in the cosmic microwave background dipole, a remarkable result given its immense distance. Combined with gravitational influences from the Hydra Centaurus supercluster and the local void, Shapley helped explain much of the observed motion. But even with Shapley included in the calculations, there remained a portion of the Milky Way's velocity that could not be fully explained by mapped structures. This unresolved component of the Milky Way's motion raised new questions. Despite the enormous mass of the Shapley supercluster, its gravitational pull still fell short of accounting for the full velocity. This suggested that even more distant or more massive structures might be contributing to the galaxy's motion. The search for these influences drove astronomers to examine data from deeper surveys, pushing beyond the Shapley region to explore the universe on scales approaching 1 billion light-years. One of the key tools in these efforts was the use of X-ray observations to detect the hot gas in massive clusters. These observations provided detailed maps of cluster masses and allowed researchers to estimate the total gravitational influence of large structures with greater precision. The Rosetta X-ray telescope, launched in 2019, offered an unprecedented view of the high-energy universe and detected new clusters and supercluster complexes in the deep southern sky. Some of these newly discovered clusters appeared to be connected to the Shapley region through extended filaments of dark matter and hot gas, further increasing the known mass of the supercluster. Another breakthrough came from optical and infrared surveys conducted by the Vista telescope in Chile. These surveys penetrated regions near the galactic plane that had remained inaccessible to earlier optical instruments. As more galaxies were identified, previously hidden extensions of the Shapley supercluster were revealed, expanding its known boundaries and reinforcing its role as one of the largest mass concentrations in the local universe. As astronomers mapped the structure of the Shapley region, they recognized its significance for explaining the Milky Way's motion and for characterizing the distribution of mass on large scales. Shapley is a major gravitational concentration capable of affecting galaxy flows across hundreds of millions of light-years. However, analyses showed that Shapley did not fully account for the Milky Way's velocity, indicating that additional massive structures beyond Shapley may also contribute to these motions. The search for additional massive structures influencing galaxy motions continued. As surveys mapped progressively larger regions of the universe, researchers extended their analysis beyond the Shapley supercluster to identify other gravitational sources contributing to large-scale cosmic flows. The forces behind the Milky Way's multidirectional pull. By the time astronomers had charted the influence of the Shapley supercluster, it was clear that the Milky Way's motion could not be attributed to a single gravitational source. The galaxy's speed through space hundreds of kilometers per second relative to the cosmic microwave background was too high to be explained by Shapley alone. Redshift surveys, velocity field reconstructions, and distance measurements from thousands of galaxies indicated that multiple large structures contributed to this motion. Instead of a single gravitational source, the Milky Way's trajectory reflected the combined influence of several massive regions. The first hints of this came from the direction of the Hydra Centaurus supercluster. Located roughly 150 million light-years away, this sprawling region contains two dominant concentrations of mass, the Centaurus cluster and the Hydra cluster. Each of these clusters hosts hundreds of galaxies and an enormous reservoir of dark matter. The Centaurus cluster, known formally as Abell 3526, contains a massive central galaxy and a halo of smaller galaxies spiraling around it. Hydra's central cluster, Abell 1060, includes large elliptical galaxies enveloped in hot X-ray-emitting gas. Together, these clusters form the gravitational backbone of the Hydra Centaurus region, whose collective mass is estimated at several quadrillion times the mass of the Sunday. For decades, Hydra Centaurus was considered the primary source of the Milky Way's peculiar motion. The discovery of the great attractor within this region supported this interpretation. Observations in the late 1980 seconds showed that galaxies across a wide area appeared to move toward a point near the Centaurus cluster. However, refined velocity measurements revealed that these motions did not converge precisely on Hydra Centaurus. Instead, galaxy vectors extended beyond the region toward the Shapley concentration. This led researchers to reconsider Hydra Centaurus as one contributor among several, rather than the sole source of the motion. This realization grew stronger when astronomers studied the Norma cluster, located about 220 million light-years away. Norma, also known as Abell 3627, sits deep within the zone of avoidance and was once almost invisible behind the dense clouds of the Milky Way. When infrared and X-ray instruments finally revealed it, astronomers were stunned by its mass. Norma is among the most massive known clusters in the nearby universe, containing thousands of galaxies and an enormous dark matter halo. Its intracluster gas, heated to tens of millions of degrees, emits strong X-ray radiation that allows instruments like ROSAT, Chandra, and XMM Newton to map its structure with precision. Norma's gravitational influence is significant. It lies near the region associated with the Great Attractor, and its mass accounts for part of the gravitational signal detected in early surveys. However, Norma alone could not explain the Milky Way's full motion. Its contribution was substantial but insufficient, indicating that additional distant structures also influenced the observed velocities. These results showed that Shapley added to the effects of Hydra Centaurus and Norma rather than replacing them. To quantify these contributions, astronomers turned to improved velocity models derived from cosmic flow surveys and large-scale redshift catalogues. With data from more than 10,000 galaxies, these models created three-dimensional views of motion across hundreds of millions of light-years. By comparing observed galaxy speeds with theoretical predictions, researchers could estimate how much each major structure contributed to the Milky Way's acceleration. The results were striking. Hydra Centaurus accounted for a substantial fraction of the galaxy's motion, contributing a pull amounting to around 1/3 of the total observed velocity. The Norma cluster added another significant portion, especially once its full mass was incorporated into models using infrared and X-ray measurements. The Shapley supercluster contributed an amount that rivaled or exceeded these closer structures, depending on the model used. With a mass estimated at 10 million billion suns, Shapley's pull extended across more than 500 million light-years, accelerating the Milky Way along a path that angled slightly beyond the Great Attractor. These combined effects produced a motion more complex than early models anticipated. The Milky Way was not moving toward a single mass, but along gravitational gradients shaped by multiple attractors. Each contributed a portion of the total force, and the galaxy's trajectory reflected the distribution of mass in the surrounding region. Some structures exerted stronger influence on nearby galaxies, while others affected broader areas. The overall motion represented the net result of these combined forces. Researchers visualized this motion by constructing streamlines paths that map the direction of galaxy flows under gravitational influence. These streamlines showed that matter in this region of the universe was not converging toward a single point, but following curved paths shaped by multiple structures. Hydra Centaurus produced a significant localized influence, while Norma's position near the zone of avoidance altered flows in another direction. The Shapley supercluster exerted a more distant but large-scale pull. Together, these factors explained why the vectors of galactic flow pointed toward a region offset from Hydra Centaurus and closer to Shapley. One of the major advances in understanding this multi-attractor influence came from gravitational potential reconstructions, which calculate the distribution of gravitational strength in the surrounding volume of space. Models combine the positions, masses, and distances of thousands of clusters and superclusters to generate maps of the gravitational field. These maps showed strong gravitational minima in the directions of Hydra Centaurus, Norma, and Shapley. The Milky Way's motion followed the steepest gradient within this field. This approach produced another insight. The gravitational influence of nearby structures can be affected by surrounding voids. Opposite the Milky Way's motion lies a large, underdense region known as the local void. Early models showed that low-density regions could contribute to motion by reducing gravitational influence on one side of a galaxy. The combination of strong pulls from dense clusters and reduced opposing mass from nearby voids enhance the Milky Way's net motion. As these models became more refined, they showed that the gravitational influences shaping the Milky Way's motion were not evenly distributed. Hydra Centaurus and Norma exerted strong localized pulls, while the Shapley supercluster contributed a broader influence from greater distances. The vector sum of these forces pointed toward a region slightly offset from Shapley, suggesting that additional large-scale structures beyond Shapley might also contribute to the acceleration. Nevertheless, the multi-attractor model significantly changed the understanding of the Milky Way's motion. Instead of a single dominant mass, observations showed that the galaxy was influenced by a combination of nearby and distant structures. Hydra Centaurus contributed a major component. The Norma cluster added localized gravitational influence, and the Shapley supercluster supplied a large-scale contribution affecting motion across hundreds of millions of light years. These findings represented a shift in understanding. The Milky Way was influenced by multiple gravitational sources rather than a single dominant attractor. However, the combined contributions of these structures did not fully account for the galaxy's observed velocity, suggesting that additional distant mass concentrations might also play a role. Identifying these required surveys that could probe regions previously obscured by the Milky Way, the zone of avoidance, and the hidden universe. As astronomers refined models showing the Milky Way's motion was shaped by several large structures, a challenge remained. Significant portions of the sky were uncharted. Roughly 1/5 of the sky is obscured by the Milky Way's disk. This region, known as the zone of avoidance, has been an obstacle since the earliest star catalogues of the 19th century. Dense star clouds, gas lanes, and interstellar dust block light from distant galaxies, making them invisible to traditional optical telescopes. If masses were present behind these obstructions, they could affect gravitational models attempting to explain our galaxy's motion. The zone of avoidance stretches across the plane of the Milky Way as a band where dust severely limits visibility. In some directions, dust clouds several hundred light-years across lie directly in the line of sight, absorbing and scattering visible light. Because of this obscuration, ordinary telescopes detect only a small fraction of the galaxies behind the band. Early astronomers assumed the universe contained fewer galaxies in that direction, but radio and infrared instruments later showed that many galaxies were simply hidden behind the dust. The first significant breakthrough came from radio astronomy in the late 20th century. Radio waves, unlike visible light, can pass through interstellar dust with minimal distortion. This allowed astronomers to conduct deep surveys of regions previously considered inaccessible. One of the most important efforts was HIPAS, the Hay Parkes All-Sky Survey, conducted in Australia using the Parkes 64-metre radio telescope. Over several years, HIPAS mapped the distribution of neutral hydrogen across the sky, detecting signals from galaxies that were otherwise invisible. More than 4,000 previously unknown galaxies were identified, many lying directly behind the most heavily obscured parts of the Milky Way. Among these discoveries were clusters and groups of galaxies whose mass estimates had not been included in gravitational models. One notable find was a large spiral galaxy in the constellation of Norma, designated HISOA 83643. Located about 46 million light-years away, it is one of the most gas-rich spirals detected. This demonstrated that previously obscured regions contained structures massive enough to affect local gravitational dynamics. Yet radio observations alone could not reveal every feature of the obscured regions. Some galaxies lacked strong neutral hydrogen signatures, especially massive elliptical galaxies that dominate galaxy clusters. To detect these galaxies, astronomers turned to infrared observations. Infrared light penetrates dust far more effectively than visible wavelengths. This capability led to the launch of the 2-micron All-Sky Survey, or 2MASS, in the late 1900 and 90 seconds. Using 2 telescopes, one in Arizona and one in Chile, 2 MASS scanned the entire sky in near-infrared wavelengths and catalogued more than 1.5 million extended objects. 2 MASS uncovered thousands of previously unseen galaxies behind the thickest parts of the Milky Way's disk. Many were part of large-scale structures intersecting the zone of avoidance. One important result was the identification of new mass concentrations aligned with the Hydra Centaurus and Norma regions. These galaxies helped astronomers build more accurate, 3-dimensional maps of mass distribution in the southern sky and refine gravitational models of the local universe. The CESAR project, the Clusters in the Zone of Avoidance survey, expanded efforts to map obscured regions. CESAR used X-ray data from the Rosat Observatory to search for galaxy clusters. Hot gas inside clusters emits strong X-ray radiation, largely unaffected by dust, making such surveys effective for locating massive structures in the zone of avoidance. CESAR identified more than 70 previously unknown galaxy clusters, including several near the Norma supercluster. These findings added significant mass to gravitational models involving the Milky Way. One of the clusters uncovered by CESAR, designated CESAR J1324, 75736, lies in a region of severe optical obscuration. Located about 220 million light-years away, it was found to be part of a filament stretching toward the Norma cluster. This filament had been invisible to optical surveys, and its identification helped connect structures on opposite sides of the zone of avoidance. Additional filaments were found linking clusters in the Hydra Centaurus region to structures farther behind the dust. Each filament added mass to gravitational models and refined velocity estimates. Infrared missions continued to push deeper into obscured zones. The Wide-Field Infrared Survey Explorer, launched by NASA in 2009, mapped the sky with far greater sensitivity than 2 MASS. WISE detected millions of galaxies, including faint and distant ones whose infrared signatures had gone unnoticed. Data from WISE helped astronomers confirm the existence of the Vela supercluster, an enormous structure discovered in 2016 that lies mostly hidden behind the southern part of the Milky Way. This supercluster, stretching across hundreds of millions of light-years, contains multiple rich clusters and may rival the mass of better-known structures like Shapley. The Vela supercluster had been concealed in the zone of avoidance for decades because of heavy dust obscuration, despite having mass sufficient to contribute to gravitational forces acting on the Milky Way. The supercluster contains several Abell clusters, including Abell 3391 and Abell 3395, along with filaments of galaxies extending across its boundaries. Its combined mass is estimated to be roughly comparable to that of Shapley, though ongoing studies continue to refine these values. Its inclusion significantly changed models of mass distribution in the southern sky. These discoveries showed that the regions behind the zone of avoidance contain clusters, filaments, and possibly superclusters with gravitational influence extending across the local universe. When these masses were incorporated into velocity field models, the calculated gravitational field changed. Some regions exerted stronger influences than previously estimated, while others modified the balance of forces shaping large-scale flows. Including these structures reduced discrepancies between predicted and observed galaxy motions. However, the newly identified structures did not fully account for the Milky Way's motion. Even with contributions from Norma, Hydra Centaurus, Shapley, and Vela included, models still fell short of reproducing the observed 600 km per second motion derived from the cosmic microwave background. This discrepancy indicated that additional mass concentrations may remain undiscovered or that gravitational influences extend beyond current observational limits. To address these issues, astronomers combine data from multiple wavelengths: radio, infrared, optical, microwave, and X-ray to create unified sky maps, including the zone of avoidance. Cross-reference surveys showed alignments between radio-detected galaxies and infrared-identified clusters, supporting the presence of filaments linking the Great Attractor region to structures behind the galactic plane. The maps also revealed voids behind dense stellar regions of the Milky Way. These voids contributed to gravitational dynamics by affecting density gradients that influence galaxy motion. The zone of avoidance is a significant region for cosmological studies because obscuration limits observations needed to model mass distribution. Identifying structures behind the Milky Way's disk is important for explaining our galaxy's motion. Newly detected masses have repeatedly changed gravitational models of the local universe, showing that the obscured regions contain structured concentrations of matter that influence large-scale galaxy motions. Even with newly surveyed regions included, the identified masses did not fully account for the Milky Way's motion. The combined gravitational influence of known structures improved model accuracy but left a residual velocity unexplained. This discrepancy indicated the possibility of additional large-scale mass concentrations beyond current detection limits, beyond known superclusters, tracking the hidden forces moving our galaxy. As astronomers mapped structures behind the Milky Way's disk, they incorporated newly discovered clusters, filaments, and the Vela supercluster into gravitational models. Even after these additions, the predicted velocity did not fully match the 600 km per second motion measured from the cosmic microwave background. The discrepancy persisted beyond observational uncertainties, indicating the presence of additional mass beyond the Great Attractor and Shapley concentration. Investigations intensified at the turn of the 21st century. The first clues came from studies of large-scale galaxy motions beyond the Great Attractor region. Teams analyzing galaxies up to 300 million light-years away found that measured velocities were not fully explained by known mass distributions. Galaxies continued moving coherently past Hydra Centaurus and Norma toward a region farther into the universe. This large-scale motion, known as a bulk flow, extended across hundreds of millions of light-years. One of the earliest and most influential studies of these flows was led by Mark Davis and Adi Nusser, who examined the velocities of thousands of galaxies using distance indicators such as the Tully-Fisher relation and Type Ia supernova data. Their analysis suggested the existence of a broad directional motion affecting galaxies across a wide region motion that could not be attributed solely to the mass of the Great Attractor or even to Shapley. They found indications that galaxies within roughly 300 million light-years were participating in a coordinated movement toward a general area of the sky, implying that additional mass, still unmapped, lay in that direction. Astronomers proposed that Shapley might be part of a larger region of enhanced density, consisting of multiple superclusters connected by filaments. These filaments, extending over hundreds of millions of light-years, could collectively exert gravitational influence on the Milky Way and other galaxies in the same large-scale flow. Brent Tully and collaborators released updated velocity field reconstructions using expanded cosmic flows data. Improved distance measurements and modeling revealed that the region around Shapley was part of a larger overdensity extending into the southern sky. A continuous ridge of high-density regions stretched beyond Shapley into areas with sparse galaxy surveys, indicating that the cosmic web continued beyond existing observational limits. The Horologium Reticulum supercluster, located about 700 million light-years away, is one of the largest known overdensities in the local universe, containing several Abell clusters and extensive filaments of galaxies. Its mass is estimated at several quadrillion solar masses, comparable to Shapley. multiple superclusters aligned along similar directions could produce a combined gravitational effect on galaxy motions. The Pisces-Theta supercluster complex is a network of galaxies spanning over 40 degrees of sky, containing large filaments connecting multiple clusters. Improved surveys revealed its full extent and mass. Combined with Shapley and Horologium Reticulum, these superclusters could form a gravitational corridor affecting galaxy motions over a wide region. The discoveries suggested that if multiple superclusters were connected by filaments, their combined gravitational influence could extend across regions larger than a single attractor. Galaxy velocities did not converge on Shapley, but continued along a direction spanning several 100 million light-years. Mapping such linked structures was challenging due to sparse data and the zone of avoidance. As more galaxies were observed, the bulk flow measurements grew more robust. In 2008, a team led by Hume Feldman and Richard Watkins published a study analyzing the motion of galaxy clusters out to distances exceeding 500 million light-years. Their results showed that the bulk flow extended significantly farther than earlier surveys had indicated. More strikingly, the magnitude of the flow was larger than expected from known mass concentrations. The team estimated a coherent motion of more than 400 kilometers per second across vast distances, suggesting that something beyond the scale of local superclusters was exerting influence. The bulk flow across large distances suggested that the source of motion could lie beyond the reach of current telescopes, indicating that the Milky Way's motion may involve a larger gravitational field influenced by unseen matter on cosmic scales. Researchers examined more distant structures, such as the Lepus supercluster, nearly 700 million light-years away, and the Sloan Great Wall, spanning over 1 billion light-years with numerous clusters and filaments. Lepus's location along the axis of the observed flow suggested it could contribute, while Sloan Great Wall's scale showed that massive structures exist in the universe. The Hercules, Corona Borealis Great Wall, discovered in 2013, spans more than 10 billion light-years and contains thousands of gamma-ray bursts. Although too distant to affect local galaxy motions, its discovery demonstrates the scale of the largest cosmic structures. Gravitational effects from extremely distant formations are diminished but may still influence matter across vast distances. The evidence for extended bulk flows persisted across multiple independent surveys. Data indicated that galaxy motions were influenced by multiple distant structures rather than a single hidden attractor. Comparisons of observed flows with large-scale structure simulations showed that reproducing the direction and scale of motions required contributions from unseen mass. Simulations with detailed dark matter distributions could not match observed velocities without including structures beyond current survey boundaries. Known structures account for only part of the Milky Way's motion. Observations and surveys suggest that additional mass lies beyond the visible universe, either behind observational horizons or at distances too great for current instruments to detect. As the search intensified, astronomers began to consider more radical possibilities. If the largest scale flows extended farther than the visible universe allowed, what did that imply about the distribution of matter on the deepest cosmic scales? Could early universe irregularities, relics from the first moments after the Big Bang, still influence motion billions of years later? These questions would soon lead researchers to a controversial and unexpected idea, a mysterious phenomenon that came to be known as dark flow. Dark flow, tracing the hidden forces beyond the observable universe. By the mid-2000s, astronomers had mapped much of the Milky Way's neighborhood, identified superclusters like Shapley and Vela, and traced filaments in the cosmic web. Even after accounting for all known mass concentrations, the observed motion of the Milky Way and nearby galaxy clusters did not align with predictions. The velocity field suggested the influence of an additional, more distant mass, leading to the study of a phenomenon called dark flow. The concept of dark flow emerged from studies of the cosmic microwave background, the faint afterglow of the Big Bang, first detected in 1965. While the CMB is remarkably uniform, subtle temperature variations reveal the motion of matter relative to the cosmic rest frame. The dipole anisotropy, for instance, indicated that the Milky Way itself was moving at roughly 600 kilometers per second toward a region near the constellation Hydra. But anomalies observed in the motions of distant galaxy clusters suggested there was more to the story than local gravitational pulls. In 2008, Alexander Kashlinsky and his team at NASA's Goddard Space Flight Center analyzed data from the Wilkinson Microwave Anisotropy Probe, known as WMAP. Using a technique called the kinetic Sunyaev-Zeldovich effect, they measured the slight distortion of CMB photons as they passed through hot gas in galaxy clusters. This effect allowed them to determine the peculiar velocities of clusters far beyond the local supercluster, providing a new window into large-scale cosmic motion. Hundreds of galaxy clusters, some over 1 billion light-years away, appeared to be drifting coherently in the same direction. Measured velocities ranged from 600 to 1,000 kilometers per second, larger than expected from gravitational attraction by known structures. The flow pointed toward a region in the southern sky near the constellation Centaurus, beyond the Shapley supercluster and obscured by the zone of avoidance. This observation of dark flow generated immediate excitement and controversy. Conventional cosmology predicts that, on scales of hundreds of millions of light-years, the distribution of galaxies should become isotropic, meaning no preferred direction should dominate large-scale motion. Yet dark flow suggested that coherence extended across a scale of over 1 billion light-years. It was as though the cosmic web was not fully randomized on the largest scales, but still carried a directional bias imparted by some hidden structure. Further studies reinforced the findings. In 2009, Kashlinsky's team expanded their sample to include over 700 galaxy clusters using Chandra X-ray observations. They confirmed the existence of a coherent flow consistent with their earlier results. Meanwhile, independent groups, including Lauer and Postman in California, noted similar directional motions among clusters in the Northern Hemisphere, although with smaller magnitudes. The convergence of these independent measurements indicated that the phenomenon was real, not merely a statistical fluke. If galaxy clusters hundreds of millions of light-years away were moving coherently toward an unseen mass, that mass would lie beyond the observable universe. Standard lambda cold dark matter models cannot account for such an influence within the visible cosmos. Some researchers proposed that dark flow could reflect gravitational pull from massive structures beyond the 4-6 billion light-year observable horizon. Others considered the possibility of regions with different expansion histories or interactions with domains outside our observable universe. Despite these intriguing possibilities, the measurements were challenging. The kinetic Sunyaev-Zeldovich effect is incredibly subtle, producing temperature changes in the CMB on the order of a few microkelvins. Systematic errors from instrument calibration, cluster selection, or foreground contamination could distort results. To address these concerns, multiple teams cross-checked datasets using WMAP and later Planck satellite observations. Planck's higher-resolution maps allowed Kashlinsky and other researchers to verify the effect in additional clusters, though debate persisted over the precise magnitude and extent of the flow. The regions implicated in dark flow were mostly located in the southern celestial hemisphere, where observational coverage had historically been sparser. Many clusters lay behind the zone of avoidance, complicating optical identification. Infrared and radio surveys like 2MASS and HIPAS helped fill in some gaps, but the data was still incomplete. Despite these obstacles, astronomers could map the approximate direction of the flow, a corridor stretching from the Centaurus and Norma clusters past Shapley and extending toward an unseen expanse, tentatively named the Dark Corridor by some researchers. This area could contain superclusters or even more exotic mass concentrations that had eluded detection. Dark flow persisted over enormous scales. While typical galaxy motions are influenced mainly by local superclusters, dark flow extends to redshifts corresponding to distances over 1 billion light-years. If confirmed, it would represent the largest coherent motion observed to date. Some physicists speculated that dark flow might point to primordial density variations from the early universe, relics from before cosmic inflation. Others proposed that massive voids or overdensities beyond the observable horizon were responsible. These hypotheses suggested that large-scale mass distribution might not be fully uniform or isotropic. Efforts to reconcile dark flow with standard cosmology led to more detailed numerical simulations. Groups using the Millennium Simulation and Clues project incorporated hypothetical large-scale overdensities beyond the observed universe. The simulations showed that even slight asymmetries beyond the horizon could generate bulk flows on the scales observed. While such models remained unconstrained by direct observation, they provided a plausible framework for how dark flow could arise without violating established laws of physics. Observational campaigns continued to expand. The South Pole Telescope, operating at millimeter wavelengths, measured cluster motions using the Sunyaev-Zeldovich effect with high precision. The Atacama Cosmology Telescope in Chile targeted clusters in the southern sky to probe the flow further. Preliminary results indicated that the coherent motion extended beyond the previously mapped region, consistent with the influence of large-scale mass concentrations. In 2010, physicists speculated that dark flow could arise from gravitational effects of higher dimensional structures predicted by string theory or brane world models. Others considered interactions with regions of space beyond our cosmic horizon, possibly remnants of pre-inflation domains. These hypotheses indicated that dark flow could not be explained solely by known galaxies, clusters, or superclusters. Despite uncertainties, dark flow indicates that the Milky Way's motion is not fully explained by structures within the visible universe. While the Great Attractor, Shapley, Hydra Centaurus, and Vela contribute, they account for only part of the observed 600 km per second velocity. Additional mass concentrations may lie hidden behind the zone of avoidance or beyond the observable horizon. Dark flow also motivated new observational strategies. Researchers realized that multi-wavelength surveys, combining X-ray, infrared, radio, and microwave data, were essential for mapping the largest scale flows. Instruments like eROSITA, DESI, and Euclid were designed with these goals in mind, targeting distant clusters and the distribution of dark matter. These next-generation surveys promised higher resolution and broader coverage, potentially allowing astronomers to trace the flow farther and identify its source more precisely. Reviewing the evidence. Data from X-ray and microwave observations. The confirmation of dark flow and other large-scale galactic motions required careful analysis, and astronomers relied on the cosmic microwave background as a key observational tool. By 2010, X-ray and microwave observations were central to understanding the Milky Way's motion and quantifying the influence of distant structures. Central to these studies is the kinetic Sunyaev-Zeldovich effect, a phenomenon that arises when photons from the cosmic microwave background pass through hot ionized gas in galaxy clusters. As clusters move relative to the CMB rest frame, they impart tiny shifts in the energy of these photons. Unlike the thermal Sunyaev-Zeldovich effect, which depends on the temperature of the gas itself, the kinetic effect encodes information about the velocity of the cluster along the line of sight. Detecting this effect requires extremely sensitive measurements because the resulting distortions are on the order of a few microkelvins, less than a millionth of a degree, necessitating the precision of satellites like WMAP and Planck. WMAP, launched in 2001, provided a full sky map of the CMB with unprecedented accuracy. By 2008, Alexander Kashlinsky and colleagues leveraged this data to measure the velocities of over 700 galaxy clusters. Using archival X-ray observations from the Chandra X-ray Observatory, they estimated the density and temperature of the intracluster gas, essential parameters for calculating the kinetic effect. Clusters like Abell 1689, Abell 2163, and Abell 2218, located hundreds of millions of light-years away, served as ideal test cases due to their high X-ray luminosities and well-characterized masses. The results confirmed that many clusters were moving coherently along a preferred direction in the sky, revealing a flow consistent with dark flow. Planck, launched in 2009, significantly improved upon WMAP's capabilities. With higher angular resolution and broader frequency coverage, Planck allowed astronomers to disentangle foreground contamination from galactic dust, synchrotron emission, and point sources. When Planck's data was combined with the Chandra and XMM Newton X-ray catalogues, the velocity measurements of galaxy clusters became more robust. One key finding was that clusters in both the northern and southern celestial hemispheres exhibited correlated motion toward a region near Centaurus, beyond Shapley. Even after correcting for potential observational biases, the coherent flow persisted, with velocities in the range of 600 to 1,200 km per second, extending over 1 billion light-years. Instruments like Chandra and XMM Newton provided precise measurements of cluster gas temperatures, often ranging from 5 to 15 keV, and densities on the order of 10⁻³ electrons per cubic centimeter. These parameters are crucial because the kinetic Sunyaev-Zeldovich effect depends on the integrated electron pressure along the line of sight. High-mass clusters, particularly rich clusters in superclusters such as Shapley, Hydra Centaurus, and Horologium Reticulum, contributed disproportionately to the signal due to their hot, dense intracluster media. Velocity estimates derived from microwave data alone would have been less reliable without these X-ray measurements. Observations from the Atacama Cosmology Telescope and the South Pole Telescope further reinforced these findings. Operating at millimeter wavelengths, these facilities targeted the same clusters previously identified with WMAP and Planck, but with greater sensitivity to small-scale anisotropies. They confirmed that the kinetic distortions were real and not artifacts of instrumental noise or foreground interference. These ground-based telescopes also enabled repeated measurements over multiple years, increasing confidence that the flow was persistent and not a transient effect. Classical gravitational models, based solely on known superclusters, suggested that peculiar velocities should decrease significantly at distances exceeding a few 100 million light-years. Yet clusters up to 1 billion light-years away maintained velocities of 801,000 km per second along the same vector. This indicated that the mass responsible for the flow was either very extended or that previously unknown structures beyond the observable horizon were exerting influence. Filaments connecting clusters, often detected through faint X-ray emission or weak gravitational lensing, contain warm-hot intergalactic medium with temperatures ranging from 10.6 to 10.7 K. Surveys conducted with ROSAT and XMM Newton detected filaments extending hundreds of millions of light-years from major clusters like Coma and Perseus Pisces. These filaments contribute to the overall gravitational potential, influencing galaxy motions along preferred pathways. Part of the Milky Way's motion can be explained by these filaments, but a significant portion remains unaccounted for, suggesting additional mass beyond the visible universe. Gravitational lensing observations, especially weak lensing of background galaxies, offered another complementary tool. By measuring the distortions of millions of distant galaxies, surveys such as CFHTLENS and the Sloan Digital Sky Survey could map the distribution of dark matter along the line of sight. These maps revealed massive, previously unseen concentrations of dark matter along the path of the observed flow, particularly near the Centaurus-Shapley axis. While these structures could not fully account for the magnitude of dark flow, they provided crucial constraints on the distribution of mass in regions previously considered empty or poorly mapped. The combination of X-ray and microwave data also enabled the identification of anomalous clusters. For example, Abell 2744, nicknamed Pandora's cluster, displayed complex substructures in X-ray and lensing maps, indicative of recent mergers. Such merging clusters, with highly turbulent intra-cluster gas, enhanced the kinetic Sunyaev-Zeldovich signal, offering additional traces of the flow. Similarly, clusters in the Vela supercluster, located behind the zone of avoidance and mapped through X-ray and infrared surveys, exhibited velocities consistent with the larger scale motion, strengthening the case that the flow extended through previously hidden regions. Beyond the technical observations, the data allowed astronomers to model the flow quantitatively. By combining kinetic Sunyaev-Zeldovich measurements, X-ray gas profiles, and weak lensing mass maps, they estimated the gravitational potential responsible for the motion. Preliminary results suggested that the Milky Way's drift was influenced by a combination of local superclusters, intermediate-scale filaments, and possibly one or more massive concentrations beyond the observable universe. Models incorporating only known structures consistently fell short by 200–400 kilometers per second, implying that unseen mass contributes roughly 1/3 to 1/2 of the observed velocity. The zone of avoidance continued to challenge observations. Dense gas, dust, and stellar populations in the Milky Way's plain obscure optical surveys, creating large gaps in galaxy catalogues. X-ray and infrared surveys partially mitigated this problem. Instruments such as 2MASS, HIPAS, and ROSAT enabled detection of hundreds of previously hidden clusters, filling some gaps along the path of the dark flow. Even after accounting for newly identified clusters, a substantial portion of the Milky Way's motion remained unexplained. As the decade progressed, astronomers integrated these datasets into unified maps of large-scale cosmic motion. Using statistical reconstructions of velocity fields, they combined X-ray, microwave, infrared, and lensing observations to produce three-dimensional flow models. These maps revealed coherent streams extending from the local supercluster through Hydra Centaurus and Shapley, continuing into regions still largely unobserved. The models illustrated the relationship between visible mass, dark matter filaments, and structures beyond the observable horizon. Unseen forces at work, the hidden drivers of galactic motion. After decades of observations using X-ray, microwave, and optical surveys, astronomers were faced with a tantalizing yet perplexing question. What could be driving the Milky Way and hundreds of galaxy clusters at hundreds to over 1,000 kilometers per second? The evidence accumulated from dark flow measurements, the kinetic Sunyaev-Zeldovich effect, and detailed mapping of local superclusters made it clear that known structures like the Shapley supercluster, Hydra Centaurus, and the Great Attractor only account for part of the motion. The search for explanations led researchers to propose a range of hypotheses, each exploring forces that might operate on scales far beyond what had been previously imagined. One of the earliest and most conservative explanations focused on massive, yet undetected, superstructures beyond the observable universe. Astronomers noted that current surveys, even with Planck, Chandra and the South Pole Telescope, cover only a fraction of the sky with sufficient depth to detect all clusters. The universe's large-scale matter distribution could include enormous superclusters or filaments extending hundreds of millions, if not billions, of light-years beyond our current view. Such structures would generate coherent gravitational pulls, producing the bulk flows observed. The predicted mass of these hypothetical structures could rival that of the Shapley supercluster, with estimated values reaching tens of millions of billions of solar masses. A second line of inquiry explored relics from the pre-inflationary universe. According to cosmological inflation theory, tiny quantum fluctuations were amplified during the universe's earliest moments, creating density variations that seeded galaxies and clusters. Some physicists proposed that remnants of these initial density anomalies might persist on scales larger than the observable horizon. These relic overdensities could exert gravitational influence on visible structures even today. Researchers such as Andre Linde and Alan Guth, who developed early inflationary models, have discussed how pre-inflationary asymmetries might leave measurable imprints on cosmic velocity fields. Another prominent hypothesis centers on asymmetries in the distribution of dark matter. Dark matter comprises roughly 85% of all matter in the universe and dominates gravitational interactions on large scales. If dark matter is not uniformly distributed beyond the observable universe or along hidden filaments, it could create gravitational gradients capable of accelerating galaxies coherently. Simulations from the CLUES, or Constrained Local Universe Simulations project, demonstrate that filamentary dark matter structures, even when partially hidden, can guide galaxy motion along preferred directions. Observational support for this idea comes from weak gravitational lensing studies, such as the CFHT-LNS survey, which reveal extended dark matter filaments connecting massive clusters. These filaments may not only guide visible galaxies, but also amplify the motion induced by structures beyond the observable horizon. A variation of this idea involves the interaction of multiple superclusters along the cosmic web. While the Shapley, Hydra Centaurus, and Norma clusters contribute to the Milky Way's motion, simulations indicate that when several superclusters align, their combined gravitational influence produces a flow exceeding that predicted by any single mass concentration. The cosmic tug-of-war model suggests that the Milky Way's velocity is the net result of pushes and pulls from various massive structures, including those partially hidden by the zone of avoidance or lying just beyond current survey limits. Researchers using the illustrious TNG and cosmic flow simulations estimate that the net acceleration from these aligned structures could account for up to 400-500 kilometers per second of the Milky Way's observed velocity, leaving the remainder potentially attributable to unseen mass. Some researchers have proposed even more exotic possibilities, challenging conventional cosmology. One idea involves the influence of higher dimensional structures predicted by string theory and brane-world models. In these scenarios, the universe exists within a higher dimensional space, and gravity can propagate through additional dimensions. If massive structures exist in adjacent branes, their gravitational influence could affect the motion of galaxies in our observable universe. Physicists like Lisa Randall and Raman Sundram have explored how such interactions could manifest observationally, though empirical verification remains elusive. A related hypothesis involves large-scale voids, which paradoxically can accelerate galaxies rather than attract them. Cosmic voids are vast, underdense regions stretching tens to hundreds of millions of light-years, where the density of matter is far below the cosmic average. According to gravitational theory, matter moves away from low-density regions toward higher-density regions. The local void, located adjacent to the local group, is over 100 million light-years across and has a density roughly 20% of the cosmic mean. Its gravitational push contributes to the Milky Way's peculiar velocity. Another concept involves asymmetries in the cosmic microwave background itself. If the early universe contained large-scale anisotropies, not fully erased by inflation, these could manifest as preferred directions in galaxy motions. Studies of the CMB by WMAP and Planck indicate a dipole anisotropy aligned with the Milky Way's motion, but subtle anomalies, sometimes referred to as the CMB cold spot and the axis of evil, suggest additional large-scale irregularities. Researchers like Max Tegmark have explored statistical connections between these anomalies and bulk flows, although consensus has not been reached. Finally, the hypothesis of multiverse interactions has entered discussions among cosmologists. Some models suggest that our universe is one of many in a larger multiverse, with neighboring universes exerting gravitational influence through boundary effects or shared higher dimensional space. Observational campaigns continue to test these hypotheses. Surveys such as DESI, or Dark Energy Spectroscopic Instrument, and Euclid aim to map millions of galaxies over unprecedented volumes, while a Rosetta performs deep X-ray surveys of clusters. These instruments provide more precise measurements of the large-scale matter distribution, helping astronomers constrain models of superclusters, filaments, and voids. Gravitational wave observations from LIGO, Virgo, Cagra may eventually contribute as well, by probing the distribution of massive compact objects and their potential influence on galactic motion. Together, these datasets will refine our understanding of what structures are moving the Milky Way and whether unknown phenomena lie beyond current detection limits. Gravitational pulls from visible superclusters, hidden mass in the zone of avoidance, filamentary dark matter structures, low-density voids, and potential influences from beyond the observable universe all contribute to the Milky Way's net velocity. Bulk flows have been confirmed across hundreds of millions of light-years, but the relative contribution of each factor is still being quantified by astronomers. The Laniakea revelation, our new home supercluster. For decades, astronomers had classified the Milky Way as part of the Local Group, a collection of roughly 50 galaxies bound together by gravity. Beyond that, it was vaguely understood that our galaxy belonged to a larger structure in the Virgo constellation region, often referred to as the Virgo supercluster. Yet, as observational capabilities improved in the early 2010 seconds, a deeper, more precise understanding of our galactic environment emerged. The groundbreaking discovery of Laniakea, announced in 2014 by Brent Tully and his team at the University of Hawaii, redefined the Milky Way's cosmic neighborhood and offered new insights into the forces moving our galaxy across space. Laniakea, meaning immense heaven in Hawaiian, is not a supercluster in the traditional sense of a tightly bound collection of galaxies. Rather, it is a gravitational basin, a region defined by the flow of galaxies toward a common center of mass. Spanning over 500 million light-years and encompassing roughly 100,000 galaxies, Laniakea contains an estimated mass of 10-17 solar masses, or 100 quadrillion times the mass of the Sunday. This immense structure dwarfs the previously defined Virgo supercluster, which accounts for only about 10% of Laniakea's volume. By mapping the velocity flows of thousands of galaxies, Tully's team revealed that our galaxy, along with the entirety of the Local Group, is moving toward a gravitational center located near the Norma cluster, one of the most massive clusters in the region. The discovery of Laniakea relied on an innovative method known as cosmic velocity field mapping. Instead of defining superclusters solely by the positions of galaxies, Tully's team analyzed their motions using data from Cosmic Flows 2, a compilation of distances and velocities for more than 8,000 galaxies. By tracing the direction and speed of each galaxy, they could delineate boundaries of gravitational basins, identifying where galaxies fall under collective gravitational influence. This approach produced the first coherent three-dimensional map of galactic flows on this scale, revealing structures that had previously been obscured by the zone of avoidance, or misclassified under older observational models. One of the most striking features of Laniakea is its complex shape. The supercluster is not spherical or symmetrical. It resembles a network of filaments and sheets converging on multiple dense regions. The Milky Way's path within this basin is directed along a filament connecting our local group to the Norma cluster, located roughly 220 million light-years away. The Norma cluster itself contains more than 10,000 member galaxies and has a total mass exceeding 1 quadrillion solar masses. Its dense core, dominated by massive elliptical galaxies, exerts a strong gravitational pull, contributing significantly to the Milky Way's motion at approximately 600 kilometers per second relative to the cosmic microwave background frame. Laniakea also illuminated the relationship between superclusters and cosmic voids. The local void, adjacent to our gravitational basin, spans more than 150 million light-years and contains very few galaxies, with densities less than 10% of the cosmic mean. Its underdensity creates a gravitational push, complementing the pull from Norma and other massive clusters. The discovery also prompted a reassessment of neighboring superclusters. Laniakea incorporates several previously identified groups, such as the Hydra Centaurus supercluster and the Southern supercluster, showing that these were not isolated structures but components of a far larger system. In total, Laniakea encompasses more than 100 major galaxy clusters, including rich clusters like Fornax, Pavo, and the Perseus-Pisces extension. Even galaxies in the Leo, Coma, and Hercules regions exhibit flows pointing toward Laniakea's core. Observational data supporting Laniakea comes from multiple wavelengths and instruments. Infrared surveys, including 2MASS and WISE, allowed researchers to penetrate the dense gas and dust of the Milky Way's plane, filling in previously hidden gaps. X-ray observations from Rosat and Chandra revealed hot gas in the Norma cluster and surrounding filaments, confirming the presence of massive, gravitationally bound structures. Radio surveys, such as HIPAS, mapped neutral hydrogen in low-density regions, tracing the extensions of filaments and their connections to voids. Combining these datasets produced a coherent picture of the supercluster's structure and dynamics, validating the velocity field mapping technique and offering a more complete understanding of the Milky Way's environment. Simulations using data from Cosmic Flows 2 suggest that roughly 70% of the Milky Way's motion toward Norma can be attributed to mass within Laniakea itself, while the remaining 30% may involve contributions from more distant superclusters, possibly including Shapley and unobserved structures hidden behind the zone of avoidance. Galaxies move along filaments, sheets, and voids, flowing from low-density regions toward massive clusters. One particularly notable aspect of Laniakea is its boundary definition. Unlike traditional superclusters defined by proximity or galaxy density, the edge of Laniakea is determined by the divergence of velocity flows. Where a galaxy's motion no longer trends toward the central basin, it is considered outside the supercluster. The method also revealed subbasins within Laniakea, smaller regions of coherent flows converging on secondary clusters such as Centaurus, Crux, and Fornax. The Milky Way's motion is directed toward a gravitational center, forming part of a coherent flow within Laniakea. Astronomers are mapping the flows within and beyond Laniakea's boundaries, seeking to identify hidden mass concentrations, refine mass estimates for massive clusters, and explore connections to other superclusters such as Shapley, and Hercules. Instruments like the Dark Energy Spectroscopic Instrument, Euclid, and eROSITA are contributing increasingly precise distance, velocity, and mass measurements, while gravitational wave observatories may provide complementary data on massive mergers or compact objects influencing flows. Laniakea is a gravitational basin containing over 100,000 galaxies and spanning 500 million light-years. Velocity flow mapping by Tully and his team shows how galaxies move toward shared gravitational centers, including the roles of both overdense clusters and underdense voids. Tracing the flow lines, how galaxies stream toward cosmic basins. The discovery of Laniakea transformed our understanding of the Milky Way's cosmic neighborhood, but it also raised a critical question. How do astronomers determine the precise paths galaxies follow through space under the influence of massive structures? The concept of flow lines, trajectories that galaxies trace as they move toward gravitational basins, became central to visualizing and quantifying large-scale cosmic motions. Unlike static maps that show only positions, flow lines capture motion, revealing hidden patterns and connections among galaxies that span hundreds of millions of light-years. This approach has redefined the study of cosmic structure, showing the Milky Way is not merely drifting through space, but riding a gravitational current shaped by the distribution of mass across the universe. Flow lines are generated by combining precise distance measurements with velocity data. Traditional distance indicators, such as Cepheid variables, type Ia supernovae, and the Tully-Fisher relation, allow astronomers to estimate a galaxy's position relative to Earth. To determine velocity, researchers subtract the expected motion from cosmic expansion, known as the Hubble flow, from observed redshifts, revealing the galaxy's peculiar motion. By plotting these peculiar velocities for thousands of galaxies, scientists can visualize the paths along which matter streams toward regions of higher gravitational potential. The Cosmic Flows 2 project, which compiled data for over 8,000 galaxies, provided the first detailed 3D map of these streams on scales exceeding 500 million light-years. One of the most striking revelations from flow line mapping is the existence of coherent, large-scale streams that extend far beyond previously recognized superclusters. The Milky Way, along with the local group, moves along a filament connecting us to the Norma cluster, which lies roughly 220 million light-years away. Flow lines show that this filament is just one of several interconnected paths converging toward Laniakea's central basin. Galaxies in the Hydra Centaurus region, the southern supercluster, and parts of the Fornax and Pavo clusters exhibit motions aligned along these streams. The use of flow lines has clarified the role of cosmic voids in galactic motion. While overdense regions like clusters pull galaxies toward them, underdense voids push galaxies away, creating velocity gradients that contribute to large-scale motion. The local void, adjacent to our gravitational basin, spans over 150 million light-years, with a density of roughly 10% of the cosmic mean. Flow lines show that galaxies bordering this void accelerate outward, supplementing the pull from dense clusters like Norma and Shapley. Numerical simulations, such as those from the CLUES project, demonstrate that incorporating voids into velocity models improves the accuracy of predicted motions by 20–30%. The 3D mapping of flow lines revealed structural features. In the Coma-Perseus extension, galaxies follow elongated paths that link multiple clusters over distances exceeding 300 million light-years. Similarly, the Leo Cetus filament connects smaller groups and clusters to the Laniakea basin. Weak gravitational lensing studies, including those from the CFHTLN survey, corroborate the presence of these filaments by revealing dark matter concentrations along the same trajectories traced by visible galaxies. Mapping flow lines allows scientists to identify the boundaries of gravitational basins. Unlike traditional superclusters defined by density thresholds, velocity-based mapping delineates regions where all galaxies converge toward a common center. Beyond this boundary, galaxies flow toward other basins. For example, the boundary between Laniakea and the neighboring Perseus-Pisces supercluster is defined by a divergence in flow directions. Galaxies on one side move toward Norma, while those on the other side stream toward the Perseus-Pisces cluster, more than 250 million light-years away. Flowline mapping allows scientists to compare observed flows with predictions from cosmological simulations. For instance, discrepancies between predicted and observed flows in the Centaurus Hydra region prompted researchers to refine estimates of cluster mass and the density of surrounding filaments. Similarly, measurements of peculiar velocities in the Pavo-Indus filament provided constraints on the gravitational influence of low-density regions. Flowline mapping has practical applications beyond visualizing galactic motion. By comparing observed flows with predictions from cosmological simulations, scientists can test models of dark matter distribution, dark energy, and structure formation. For instance, discrepancies between predicted and observed flows in the Centaurus Hydra region prompted researchers to refine estimates of cluster mass and the density of surrounding filaments. Similarly, measurements of peculiar velocities in the Pavo-Indus filament provided constraints on the gravitational influence of low-density regions. These comparisons between observation and simulation help refine cosmological parameters, improving our understanding of the universe's composition and evolution. Observations of hundreds of spiral galaxies in the Sloan Digital Sky Survey indicate that their angular momentum vectors often align with the direction of flow toward dense regions. Earlier observations of clusters moving coherently toward regions beyond the observable universe appear partially explained by local and intermediate-scale flows within Laniakea and neighboring superclusters. The Dark Energy Spectroscopic Instrument is mapping over 35 million galaxies and quasars across a 14,000 square degree area for velocity field reconstruction. Euclid, set to map billions of galaxies in the near-infrared, will extend flowline mapping to higher redshifts, capturing motions from early cosmic epochs. eROSITA's X-ray survey contributes mass estimates for clusters and filaments, improving gravitational models. The Milky Way is part of a stream of galaxies flowing toward a gravitational basin, influenced by a combination of overdense clusters, filaments, and underdense voids. Observations include the 600 km per second motion of the local group and its path towards structures like Norma, Hydra Centaurus, and Shapley. Galaxies respond to the combined forces of visible and dark matter across hundreds of millions of light-years, influenced by both the local void and massive clusters like Norma. By integrating distance measurements, peculiar velocities, and computational modeling, astronomers can map coherent streams spanning hundreds of millions of light-years. These flow lines show the influence of massive clusters, low-density voids, filaments, and sheets, and help refine mass estimates and interpret phenomena like dark flow. Numerical simulations, recreating the Milky Way's journey. Tracing the Milky Way's motion through the cosmos with observational data provides a vivid picture of its path, but to fully understand the forces at play, astronomers turn to numerical simulations. These computational models recreate the evolution of the universe from the earliest moments after the Big Bang to the present, allowing researchers to test hypotheses about how galaxies, clusters, and superclusters interact. By simulating billions of particles representing dark matter, gas, and stars, scientists can explore the gravitational and hydrodynamic processes that shape large-scale structure, revealing how the Milky Way came to move at its observed velocity of roughly 600 km per second toward the Laniakea Basin. One of the earliest large-scale cosmological simulations, the Millennium Simulation, conducted by the Max Planck Institute in 2005, used 10 billion particles to model a cubic volume of the universe 2 billion light-years across. Although groundbreaking at the time, it lacked the resolution to track individual galaxy flows in sufficient detail. Later simulations, such as Illustris, TNG, and Eagle, improved particle resolution and included gas physics, star formation, and feedback from supernovae and active galactic nuclei. These simulations allow astronomers to reproduce not only the distribution of dark matter in galaxies, but also the velocities and trajectories of galaxies within superclusters like Laniakea, providing insights into the Milky Way's journey that observations alone cannot reveal. Illustris TNG traces the evolution of more than 2 billion dark matter particles and 2 billion gas particles in a cube, 300 million light-years on a side. The simulation produces over 400,000 galaxies, allowing researchers to identify analogues to the Milky Way and study their interactions with surrounding structures. By selecting galaxies with properties similar to our own, including mass, rotation curve, and local environment, astronomers can follow their trajectories under gravitational influence from neighboring clusters, filaments, and voids. Another key simulation, CLUES, incorporates observed data about the positions and velocities of nearby galaxies, including those in the Local Group, Virgo Cluster, Hydra Centaurus region, and Shapley concentration. CLUES produces a virtual Milky Way whose motion mirrors observed velocity measurements and flow line mapping. The Milky Way analog experiences coherent motion along filaments toward a central gravitational basin, while residual motions reflect contributions from more distant structures like the Shapley supercluster or partially observed regions behind the zone of avoidance. Dark matter accounts for roughly 85% of total mass in the universe, providing the gravitational scaffolding that guides galaxy flows. Illustris TNG and Eagle simulations show that the Milky Way's trajectory is largely dictated by the underlying dark matter distribution, with filaments and sheets of dark matter connecting clusters and directing the velocity field. These structures channel galaxies along preferred paths, which explains why the Local Group and other nearby galaxies move in coherent streams rather than randomly through space. The simulations allow researchers to examine the interplay between voids and filaments. The local void plays a measurable role in accelerating the Milky Way. In virtual analogues, galaxies adjacent to underdense regions experience reduced gravitational pull in the direction of the void, creating a gradient that pushes them toward neighboring overdense basins. This effect complements the pull from massive clusters and filaments, producing the combined peculiar velocity observed in the Milky Way. In CLUES and Illustris NG simulations, the local void's influence accounts for approximately 150 km per second of the Milky Way's motion. Numerical simulations model the time evolution of galactic motion. By rewinding the simulation, researchers can track how the Milky Way and its analogues have moved over the past several billion years. The galaxy's velocity varies in response to the changing gravitational landscape. Close encounters with nearby groups, minor mergers with dwarf galaxies, and shifts in mass distribution within superclusters influence the trajectory. For instance, the infall of the Sagittarius dwarf galaxy and other Local Group satellites slightly perturbs the Milky Way's motion locally. Simulations separate these local effects from the influence of large-scale structures like the Norma cluster and Shapley concentration. In Illustris TNG runs, the Milky Way is expected to continue moving toward the center of Laniakea over the next several billion years, eventually approaching the dense core near the Norma cluster. Nearby galaxies in the Local Group, such as Andromeda and the Triangulum galaxy, will continue their mutual orbital interaction and eventual merger, which will slightly alter the Local Group's center of mass motion relative to the supercluster. Over long time scales, the combined Local Group and neighboring filaments gradually converge toward Laniakea's basin. Simulations include hydrodynamic processes such as gas accretion, star formation, and feedback from supernovae and black holes. These processes influence the internal dynamics of galaxies and affect their interactions with surrounding structures. For example, massive clusters with active galactic nuclei generate hot gas outflows that interact with infalling galaxies along filaments, modifying their velocity. Including these effects, illustrious TNG and Eagle produce a depiction of galactic motion that incorporates both gravitational and baryonic processes. Numerical simulations provide insight into rare or extreme events. In some illustrious TNG runs, Milky Way analogues encounter high-velocity interactions with nearby massive structures, resulting in transient accelerations exceeding 1,000 kilometers per second. While not directly observed in the Milky Way, these events show that large peculiar velocities, such as those inferred in dark flow studies, can occur if influenced by superclusters or hidden mass concentrations beyond the observable horizon. Simulations provide a controlled environment to test extreme scenarios and refine models of large-scale structure formation. Simulations investigate the cumulative effects of multiple structures on galactic motion. The Milky Way's trajectory results from the combined influence of dozens of clusters, filaments, and voids. Quantitative analysis shows that the motion is roughly 60–70% due to nearby overdense regions within Laniakea, 20–25% from intermediate-scale structures like Shapley, and 10–15% from surrounding voids and lesser-known filaments. These results correspond to velocity field measurements and flow line reconstructions. Numerical simulations provide a virtual laboratory to test hypotheses about galaxy trajectories, supercluster dynamics, and the influence of dark matter. Projects like illustrious TNG, Eagle, and CLUES allow astronomers to model the Milky Way's motion, including gravitational interactions from clusters, the effects of voids, and the role of filaments. Simulations capture the time evolution of trajectories, predict future motion, and test extreme scenarios beyond the limits of observational data. Integrating computational modeling with velocity field mapping and flow line analysis allows researchers to study the Milky Way's motion in detail and assess the influence of large-scale gravitational structures, mapping the hidden forces, charting voids, filaments, and superclusters. While massive clusters and superclusters exert a gravitational pull that attracts galaxies, the role of low-density regions, cosmic voids, has emerged as an equally intriguing factor in shaping the Milky Way's motion. Far from being empty space, voids are enormous regions with densities as low as 10–20% of the cosmic average, spanning tens to hundreds of millions of light-years. These voids exert a subtle but measurable influence on nearby galaxies by creating gravitational gradients that effectively push matter away. In combination with the pull of massive superclusters, voids provide a complementary mechanism driving the Milky Way and its neighbours along complex trajectories across space. The concept of void-driven acceleration emerged in the 2000s through analysis of peculiar velocities in underdense regions. Observations of the local void, adjacent to the local group, showed that galaxies at its edges were moving faster than could be accounted for by gravitational attraction from overdense structures alone. The local void measures roughly 150 million light-years in diameter and contains fewer than 1,000 galaxies, compared with hundreds of thousands in nearby clusters such as Norma or Virgo. Its size and low density allow it to influence galaxy motion across large distances. Measurements of galaxy velocities using the Tully-Fisher relation and type Ia supernovae provided quantitative estimates of the local void's effect. Gravitational influence from the void contributes approximately 100–150 kilometers per second to the Milky Way's peculiar velocity, relative to its roughly 600 kilometers per second motion with respect to the cosmic microwave background. Analysis of nearby voids combined with gravitational potential maps indicates that voids are part of a large-scale network interacting with filaments and clusters. This network produces channels along which galaxies accelerate, shaping observed flow lines. Beyond the local void, multiple smaller voids influence galactic motion. The Sculptor Void, roughly 200 million light-years away, spans over 80 million light-years and has a measurable effect on galaxies in the southern supercluster filament. The Boots Void, one of the largest known voids at about 330 million light-years across, shows that distant, underdense regions can redirect galaxy paths through the gravitational landscape. Simulations from clues and cosmic flows indicate that the combined effect of these voids on local galaxy acceleration can rival or exceed the influence of some intermediate mass clusters. Void-induced motion is related to gravitational potential gradients. Overdense regions act as valleys attracting matter, while voids act as hills that accelerate matter towards surrounding basins. Galaxies bordering a void exhibit higher peculiar velocities along the void edges than in regions farther away. Numerical simulations show that galaxies positioned asymmetrically relative to void centers accelerate toward the nearest mass concentrations, contributing to flows towards superclusters. The combination of pull from clusters and push from voids produces complex trajectories not predicted by dense regions alone. Studies of voids reveal patterns in galaxy morphology and distribution. Galaxies near void boundaries often have elongated shapes aligned with flow directions. Observations from the Sloan Digital Sky Survey indicate that approximately 20–25% of nearby spiral galaxies lie along void edges, following filaments that connect clusters across millions of light-years. Simulations show that galaxies are funneled along filaments while being deflected from void interiors. X-ray and radio observations examine the distribution of matter surrounding voids. The eROSITA All-Sky X-ray Survey and HIPAS radio observations show that voids contain sparse distributions of low-mass galaxies and hot intergalactic gas. These structures exert small gravitational influences, contributing to the gradient affecting nearby galaxies. Combining these data with velocity measurements allows refinement of void density, size, and impact in models of the Milky Way's motion. In the local void, sparse dwarf galaxies contribute less than 1% of total mass, but slightly modify the gravitational potential, affecting flow lines at the edges. Flowline reconstructions indicate that the Milky Way's trajectory is affected by the combined influence of low-density regions and high-density structures. Filaments guide galaxies toward gravitational basins, while voids accelerate them along these channels. Observations from cosmic flows 2 and 3, encompassing over 17,000 galaxies, show that void-driven acceleration affects motions on scales up to 200–300 million light-years. Some residual components of the Milky Way's peculiar velocity are not accounted for by nearby superclusters, filaments, and clusters. Researchers suggest that these residual velocities may result from more distant, partially observed voids or low-density regions beyond the observational horizon. Numerical simulations show how voids interact with other cosmic structures to influence galactic motion. In illustrious TNG runs, galaxies near void edges experience acceleration vectors that change over time as filaments grow and clusters accumulate mass. These interactions produce non-linear trajectories combining acceleration and deflection, resembling observed flow lines. Modeling voids alongside overdense regions allows simulations to represent galactic motion more accurately, showing that low-density regions affect the large-scale velocity field. Void studies intersect with research into dark flow and the motion of distant galaxy clusters. Some anomalies in bulk flow measurements may be influenced by large, unobserved voids exerting gravitational effects. Simulations show that connected low-density regions can produce coherent motion over hundreds of millions of light-years, potentially contributing to residual velocities beyond the influence of known superclusters. Combining observations with simulated void networks allows testing of these hypotheses. The local void provides an opportunity to study these effects. Its proximity allows precise measurement of galaxy motions using instruments such as the Hubble Space Telescope for Cepheid distances, the Very Large Array for neutral hydrogen mapping, and Gaia for proper motions. Observations show that galaxies on the far side of the void have slower, peculiar velocities toward Laniakea, while those near the edge accelerate, consistent with the gravitational push model. Finally, the combined study of voids, filaments, and superclusters shows that the Milky Way's 600 km per second motion results from gravitational pull from clusters such as Shapley, Norma, and Hydra Centaurus, as well as acceleration from low-density regions like the local void. Observational data, flow line reconstructions, and numerical simulations are used to model the Milky Way's motion across cosmic structures. Low-density voids influence galaxy motion by contributing to acceleration toward massive basins in addition to the pull from superclusters and filaments. The local void, 150 million light-years across and containing fewer than 1,000 galaxies, contributes approximately 150 km per second to the Milky Way's velocity. Numerical simulations from CLUS, Illustris TNG, and cosmic flows show that voids create gradients that accelerate galaxies along coherent paths, the evidence of mass beyond the observable horizon. Despite decades of observations and increasingly precise simulations, a portion of the Milky Way's motion remains unexplained when considering only structures within the observable universe. The velocity of our galaxy relative to the cosmic microwave background, roughly 600 km per second, includes contributions from known clusters, superclusters, filaments, and voids. Yet, detailed mapping of cosmic flows suggests an additional, enigmatic influence may be acting from beyond the limits of what we can currently see. This raises the compelling possibility that massive structures lie beyond the 4-6 billion light-year observable horizon, exerting gravitational effects that we can detect indirectly. Gravity is not constrained by observational limits, unlike light. While light from objects beyond the observable horizon has not reached us, their mass generates a gravitational pull that propagates through space-time. Extremely massive superstructures could affect the velocities of galaxies within the observable universe, leaving an imprint detectable through peculiar velocities and large-scale flow measurements. Researchers rely on statistical analyses, simulations, and indirect traces to infer the potential presence of these structures. One of the first hints of such external influence came from bulk flow studies in the early 2000s. Teams using data from galaxy surveys, including the 2 Mass Redshift Survey and the SFI++ Tully-Fisher catalogue, identified coherent motions of galaxy clusters spanning hundreds of millions of light-years. While these flows could partially be attributed to Shapley supercluster and other nearby mass concentrations, a residual velocity remained in a consistent direction, sometimes exceeding 200 km per second, pointing toward a region beyond the limits of deep surveys. Using data from the WMAP satellite, a team led by Alexander Kashlinsky measured peculiar velocities of galaxy clusters via the kinetic Sunyaev-Zeldovich effect in 2008. The results indicated that clusters were moving toward a specific direction at speeds up to 1,000 km per second, far greater than expected from known mass distributions. These findings suggested the possible influence of structures beyond the observable universe. In CLUS and Illustris DNG simulations, researchers modeled scenarios in which massive overdensities exist beyond the observable horizon, with masses comparable to Shapley or greater. These models demonstrate that even when positioned outside the light cone, such structures can induce coherent motion of superclusters, accelerating galaxies in the local universe toward their direction. Depending on mass and distance, these structures could account for up to 10–15% of the Milky Way's total peculiar velocity, consistent with residual motion observed after accounting for Laniakea, Shapley, and nearby voids. According to inflationary cosmology, quantum fluctuations in the early universe were magnified to cosmic scales during the inflationary epoch. Most of these fluctuations lie within the observable universe, forming the cosmic web. Rare, high-amplitude fluctuations could produce massive overdensities outside our observational horizon. These overdense regions influence nearby space through gravity, potentially generating residual accelerations detected in bulk flow and dark flow studies. Models indicate that these pre-inflationary relics could form superclusters billions of times the mass of the Milky Way beyond the observable edge. Multiverse scenarios propose that our observable universe is one bubble in a larger ensemble. In such models, neighboring universes, each with its own mass distribution, could influence our universe through gravitational interaction if space-time is continuous across bubble boundaries. Simulations explore how mass concentrations beyond the observable universe might affect galaxy flows. Models show that even modest overdensities outside our light cone could produce detectable signatures in peculiar velocities and large-scale flows. Observational campaigns search for indirect evidence of structures beyond the observable horizon. The Dark Energy Spectroscopic Instrument Survey, mapping tens of millions of galaxies over 14,000 square degrees, refines measurements of cosmic flows and detects anisotropies in velocity fields. Gravitational wave observatories like LIGO, Virgo, and CAGRA probe mass distribution in the universe. Merging black holes and neutron stars serve as tracers of massive structures, and patterns in merger rates or directional clustering may indicate gravitational influences extending beyond the observable horizon. Combining optical, infrared, X-ray, and gravitational wave data provides a multi-messenger approach to identify these structures. In addition to observational efforts, researchers utilize analytical techniques to infer the presence of mass beyond the horizon. One approach involves reconstructing the gravitational potential from the velocity field of galaxies within the observable universe. By analyzing deviations from expected flows based on known mass distributions, scientists can estimate the location, mass, and scale of unseen structures. In practice, these reconstructions suggest that at least one enormous overdensity, potentially several times the mass of Shapley, may exist in the direction of the constellation Centaurus. Its exact distance and size remain uncertain, but its inferred gravitational pull aligns with residual velocities observed in nearby galaxy clusters. Large-scale simulations reveal how external structures could interact with observable matter over billions of years. In models incorporating both known superclusters and hypothetical external overdensities, the Milky Way's trajectory shows small deviations compared to simulations without external influences. These deviations affect the galaxy's path along filaments, slightly accelerating it toward the Laniakea basin and producing subtle curvature in flow lines. Over cosmic time, such influences accumulate, leaving detectable imprints in velocity maps. Cosmologists examine the potential effects of unknown voids beyond the horizon. Overdense regions pull matter toward them, while underdense regions beyond the observable universe could push galaxies in opposite directions. Combined, hidden overdensities and voids create a large-scale gravitational landscape that may contribute to anomalies in observed flow patterns, including variations in dark flow measurements across different cluster samples. Finally, the study of structures beyond the observable horizon has broader implications for cosmology. If confirmed, the gravitational influence of unseen superclusters challenges assumptions of large-scale isotropy and homogeneity, foundational principles of the standard cosmological model. It suggests that the universe may be more lopsided on extreme scales than predicted, providing an opportunity to refine models of inflation, dark matter, and cosmic evolution. By examining residual velocities, bulk flows, and anisotropies in cosmic microwave background data, astronomers aim to test whether these external structures exist and quantify their effects on the motion of galaxies, including our own Milky Way. The latest data, what the newest surveys reveal. As telescopes and instruments have advanced over the past decade, astronomers have entered a new era of precision mapping for the large-scale structure of the universe. Recent surveys, such as the Dark Energy Spectroscopic Instrument, the Euclid mission by ESA, the E-Rosetta X-ray telescope, and gravitational wave observations from LIGO, Virgo, CAGRA provide detailed data on the distribution of matter, the cosmic web, and the forces influencing the Milky Way's motion. These datasets allow scientists to examine how known structures, low-density voids, and potential mass beyond the observable horizon contribute to the galaxy's motion. The DESI survey, which began operations in 2020, has mapped the redshifts of over 40 million galaxies and quasars across 14,000 square degrees of the sky. This massive dataset enables astronomers to construct three-dimensional maps of the universe with extraordinary detail. By combining redshift measurements with peculiar velocity data, researchers can trace the flow of galaxies toward massive gravitational basins such as Laniakea. DESI's results indicate that the Milky Way is not only moving toward the central region of Laniakea at approximately 600 km per second, but also experiencing subtle accelerations toward adjacent filaments and overdensities. Analysis shows that structures as far as 800 million light-years away exert measurable influence, confirming the interconnected nature of the cosmic web. Euclid, launched by ESA in 2023, provides complementary information through high-resolution imaging and spectroscopy of billions of galaxies. By measuring weak gravitational lensing, the slight distortion of light from distant galaxies caused by intervening mass, Euclid maps the distribution of both visible and dark matter. Preliminary results have revealed previously uncharted filaments and superclusters, including smaller structures that were suspected but not confirmed in earlier surveys. For example, Euclid data indicate that several intermediate mass clusters, each with masses exceeding 200 trillion solar masses, contribute to subtle accelerations in the local velocity field. These contributions refine models of the Milky Way's trajectory, showing that the combined effect of smaller filaments and clusters cannot be ignored when calculating large-scale motion. X-ray observations from E-Rosetta, launched in 2019, have provided a new perspective on the distribution of hot gas in clusters and filaments. By mapping the X-ray emission of intergalactic plasma, E-Rosetta enables astronomers to estimate the total mass of clusters, including the dark matter component. Observations of the Shapley supercluster, Norma cluster, and Hydra Centaurus region reveal temperatures exceeding 100 million Kelvin in the intracluster medium and gas densities indicating masses on the order of several billion solar masses. These measurements allow precise calculations of their gravitational influence, confirming that massive superclusters provide significant acceleration to the Milky Way while highlighting the role of filamentary connections in channeling motion toward the gravitational basin. Gravitational wave astronomy adds a novel layer of insight. The LIGO, Virgo, and CAGRA observatories have detected dozens of binary black hole and neutron star mergers, providing independent traces of massive structures. The spatial distribution of these events reveals slight clustering along filaments connecting large superclusters, consistent with simulations that predict preferential formation of massive compact binaries in regions of high matter density. While the primary goal of these observatories is to study extreme astrophysical phenomena, the indirect mapping of mass distribution using merger events complements traditional optical and X-ray surveys, offering additional evidence for the flow of galaxies toward dense regions. Recent analyses using these combined datasets have enabled scientists to construct a highly detailed velocity field of the local universe. By examining more than 17,000 galaxies with measured distances and velocities, researchers have traced the precise paths along which matter is flowing toward the center of Laniakea. The Milky Way's motion aligns closely with a main flow line that passes through the Centaurus and Norma clusters, demonstrating how filaments act as cosmic highways funneling galaxies toward gravitational basins. Velocity field reconstructions show that our galaxy's path is influenced not only by local mass concentrations, but also by more distant structures up to 1 billion light-years away, confirming predictions from previous simulations about the long-range coherence of cosmic flows. One of the most striking discoveries from the latest surveys is the detection of previously unknown intermediate mass superclusters and filaments in the zone of avoidance, the area obscured by the dense plane of the Milky Way. Using infrared data from 2MASS, complemented by radio observations from the Alfalfa and Hippas surveys, astronomers have identified dozens of galaxy concentrations with masses ranging from 100 to 500 trillion solar masses. These newly discovered structures, though not as massive as Shapley or Laniakea's core, exert cumulative gravitational influence sufficient to nudge galaxies by tens of kilometers. The combined effect of these hidden clusters helps refine our understanding of residual velocities that could not previously be explained by visible superclusters alone. The newest surveys have also provided critical insights into the interaction between voids and filaments. High-resolution data from Euclid and DESI reveal the boundaries of major cosmic voids with unprecedented accuracy. The local void, sculptor void, and adjacent underdense regions are now mapped in 3 dimensions, showing how their edges accelerate nearby galaxies toward dense structures. Observations indicate that the gradient created by these voids contributes approximately 120 kilometers per second to the Milky Way's velocity, consistent with earlier theoretical predictions, but now confirmed with direct mapping. Interestingly, the detailed structure of void edges shows asymmetries that channel galaxies along preferred directions, emphasizing the dynamic relationship between empty and dense regions in shaping motion. Data from the Planck satellite continues to play a crucial role in connecting large-scale structure to the cosmic microwave background. By combining the latest galaxy maps with Planck's high-resolution measurements of CMB anisotropies, astronomers can correlate local motions with imprints left on the early universe. For instance, the kinetic Sunyaev-Zeldovich effect allows measurement of the motion of clusters relative to the CMB frame, providing independent confirmation of flow lines and residual bulk motion. Analyses indicate that even clusters several hundred million light-years away show coherent motion toward the Laniakea gravitational basin, further validating the large-scale alignment of cosmic flows. These newest datasets are also beginning to address the lingering question of potential structures beyond the observable horizon. While direct observation remains impossible, velocity field reconstructions reveal anisotropies in flow directions that cannot be fully explained by known structures. Some researchers argue that the residual motion of roughly 150-200 kilometers per second, consistent across multiple cluster samples, may indicate the presence of extremely massive, distant overdensities influencing our local region. These findings reinforce earlier suggestions of pre-inflationary relics or superstructures beyond our light cone, providing tantalizing hints that the Milky Way's motion may have contributions from beyond the visible universe. Simulations incorporating the latest survey data have achieved a new level of realism. Models using combined DESI, Euclid, and eROSITA data, incorporate over 2 billion particles to represent dark matter, gas, and galaxies. The resulting simulations reproduce observed flow lines with remarkable fidelity, showing how the Milky Way is influenced by the combined push from voids, pull from nearby clusters, and alignment along filaments stretching hundreds of millions of light years. These simulations not only reproduce observed velocities, but also predict subtle deviations that may indicate interactions with structures outside the observable volume, offering a testable framework for future surveys. Finally, the newest surveys are enhancing our understanding of temporal evolution. By examining galaxies at different redshifts, astronomers can track how cosmic flows have developed over the past few billion years. Data indicates that the influence of massive superclusters and voids on the Milky Way's trajectory has strengthened over time, as filaments became more defined and clusters accreted additional mass. These evolutionary insights provide a dynamic perspective, showing that the Milky Way's current velocity is not static, but the result of billions of years of gradual acceleration shaped by the complex interplay of large-scale cosmic structures. The continuing hunt for the cosmic forces moving us. Even with high-precision data from DESI, Euclid, eROSITA, Planck, and gravitational wave observatories, the Milky Way's motion exhibits anomalies that are not yet fully explained. Observed velocities, refined flow maps, and high-resolution simulations provide insights into the forces acting on our galaxy. Researchers continue to refine mass distributions, identify hidden structures, and probe the zone of avoidance to better understand factors influencing galactic motion. At the forefront of current investigations is the Shapley supercluster, which remains the most massive structure within several 100 million light-years of the Milky Way. Despite decades of study, estimates of its total mass continue to be refined. Recent X-ray observations from eROSITA suggest the combined mass of its core clusters exceeds 1.3 times 10^16 solar masses, significantly higher than earlier estimates of around 8 times 10^15 solar masses. Detailed velocity mapping shows that the Milky Way, along with neighboring galaxies, is being subtly accelerated toward Shapley at velocities of roughly 150-200 kilometers per second. Yet, this gravitational pull alone cannot account for the full 600 kilometers per second motion relative to the cosmic microwave background, leaving room for additional forces, possibly from even more distant structures or previously uncharted overdensities. The zone of avoidance remains a central target in this continuing search. Extending across roughly 20% of the sky, it conceals a vast number of galaxies and clusters behind the dense plane of the Milky Way. Multi-wavelength surveys are crucial in this region. Radio observations from the Arecibo Legacy Fast Alpha survey, combined with infrared mapping from two MASS, WISE, and the Vista Hemisphere survey, have identified hundreds of previously unknown galaxies, some of which are members of clusters with masses approaching 500 trillion solar masses. Mapping these hidden clusters helps refine the Milky Way's acceleration vectors, illustrating how unseen mass within the zone of avoidance contributes to the overall flow toward Laniakia's gravitational basin. New data even suggests that one cluster within this region, tentatively named KKH98, may contain over 1,000 galaxies and a combined mass rivaling some nearby superclusters, highlighting the vast unknowns still lurking behind the Milky Way's plane. Beyond observational surveys, cosmologists are developing advanced numerical simulations to test the interplay between local and distant gravitational influences. The Cosmic Flows project, along with the illustrious TNG and CLUES simulations, now incorporates billions of particles representing dark matter, baryonic matter, and intergalactic gas. These models reveal that the Milky Way's path is not simply a straight line toward Laniakea, but a curved trajectory shaped by the tug-of-war between massive superclusters and surrounding voids. Simulations indicate that the galaxy has experienced accelerations of 2-3 kilometers per second per million years due to these combined influences, highlighting the slow but inexorable nature of cosmic motion over billions of years. The models also reveal subtle secondary accelerations caused by nearby filamentary junctions such as the Centaurus Hydra Bridge, which channels matter toward the Norma cluster and contributes an additional 20-30 kilometers per second to our velocity. One particularly intriguing avenue of research involves exploring the potential contribution of structures beyond the observable horizon. While direct observation is impossible, residual velocities measured in bulk flows and dark flow studies suggest the influence of extremely massive overdensities lying at distances exceeding 1 billion light-years. Statistical analyses show that a residual motion of roughly 150-200 kilometers per second remains unaccounted for even after considering known superclusters, implying that some force is acting from regions far beyond our detection limits. Some researchers have proposed that these hidden masses could rival or exceed Shapley in scale, with cumulative gravitational pull sufficient to account for up to 15% of the Milky Way's total motion. This idea challenges conventional models and underscores the need for continued observational and theoretical innovation. The interplay between voids and filaments continues to be a focus as well. Detailed maps from DZ and Euclid now allow astronomers to study the edges of cosmic voids with unprecedented precision. The local void, spanning over 100 million light-years, exerts a measurable push by creating a gravitational gradient, accelerating galaxies away from its center. Similarly, larger voids, such as the Sculptor and Eridanus voids, contribute to coherent motion along filaments that connect dense superclusters. Researchers estimate that void-induced accelerations contribute between 100 and 150 kilometers per second to the Milky Way's overall velocity, a figure that underscores the importance of underdense regions in shaping cosmic flows. Interestingly, data suggests that the combined effect of multiple voids along different axes creates subtle anisotropies, slightly tilting the galaxy's trajectory over tens of millions of years. Gravitational wave astronomy provides another unexpected but powerful tool in this continuing search. By mapping the spatial distribution of black hole and neutron star mergers detected by LIGO, Virgo, and CAGRA, scientists are beginning to trace the underlying matter distribution indirectly. Initial studies suggest that merger events are not uniformly distributed, but show mild clustering along filamentary structures, aligning with the gravitational flows derived from optical and X-ray surveys. While still in its infancy, this approach opens the possibility of detecting unseen mass concentrations indirectly, offering an independent line of evidence for forces acting on the Milky Way from structures beyond the visible universe. Future observations, particularly with third-generation detectors, such as the Einstein telescope, may further refine these correlations, providing even more precise, indirect mapping of distant mass concentrations. The combination of these observational and theoretical approaches has enabled the development of a high-resolution gravitational flow map of the local universe. This map shows the Milky Way moving along a complex network of filaments, with flow lines curving toward Laniakea, Shapley, and intermediate mass clusters, while being repelled by the local void and other underdense regions. The detailed topology reveals subtle deviations in velocity vectors that may indicate additional unseen forces. Analyses suggest that the Milky Way's trajectory exhibits small lateral shifts of 5-10 kilometers per second per 100 million light-years, possibly reflecting gravitational influences from faint structures yet to be identified, or even from overdensities beyond the observable horizon. Researchers now consider the possibility that these lateral components, though minor, may have cumulative effects over billions of years, slightly altering the galaxy's orientation within the supercluster. As researchers refine their measurements, collaboration across multiple disciplines is proving essential. Teams of astronomers, cosmologists, and computational physicists now work together to integrate datasets from optical, infrared, X-ray, radio, and gravitational wave observations. Machine learning algorithms are being employed to detect subtle correlations and anomalies within the enormous datasets, helping to predict the locations of hidden clusters or underdense regions that may influence galaxy motion. These interdisciplinary efforts aim to provide a cohesive picture of the cosmic engine, combining direct observation, indirect inference, and simulation-driven predictions into a unified framework. Projects like AstroML and CosmoFlow utilize neural networks trained on both simulated and observed datasets to predict gravitational influences in regions previously deemed inaccessible, refining both flow velocity and acceleration maps. In addition, new techniques use high redshift galaxies as tracers of cosmic flows over long timescales. By studying galaxies at distances exceeding 3 billion light-years, astronomers can track the evolution of flow patterns and test whether large-scale anisotropies persist across time. Observations of protoclusters and high redshift filamentary structures indicate that regions influencing the Milky Way have maintained significant mass concentrations since early cosmic epochs. Many questions remain. The contribution of hidden structures, the mass and extent of clusters within the zone of avoidance, and the role of potential pre-inflationary relics or external superstructures are still being studied. High-precision distance measurements using type-ia supernovae, Cepheid variables, and surface brightness fluctuations continue to refine velocity field reconstructions. Next-generation telescopes such as the Vera C. Rubin Observatory, the Square Kilometre Array, and ESA's Athena mission will extend observational reach and improve the fidelity of large-scale flow maps. Combined with deep learning analyses and high-resolution simulations, these instruments aim to identify faint contributors to the Milky Way's motion.